Okay, you should be able to hear. You should be able to hear me now. I'm so sorry. Well, that was. I was super excited. we had forward momentum. I was like, yeah, let's go, woo! And then, yeah, it ended up being that no one could hear me, which is fine. Totally fine. Like, not a problem. Thanks for letting me know. Okay. Right. So, what's going on? So, as you can see from the stream title, today we are continuing what we worked on yesterday, which was a four-dimensional galaxy simulator. Let's talk about what we know, what we're going to do, and where we're going to go. So, 4D galaxy simulator. Now, I mentioned yesterday that my particular research focus is not so much in the 4D-ness or the galaxy-ness of this simulation, but in the n-body-ness of the simulation. The idea is that I want to focus on making a better n-body simulator. The reason I want to do this is because it actually ties into a bunch of other research that I've been doing recently in combining the areas of computer graphics and computational physics together. 20 seconds behind. Also, I think it's fine. There might be a video audio delay. I don't know. We'll figure that out. Anyway, I can fix that, I think, pretty quickly now. So, yesterday, we actually went about creating our n-body simulator, which worked pretty well. We got it working at the last moment, just in the nick of time yesterday, but we didn't have time to do any plotting or anything like that. So today, I'm going to basically take the n-body simulator and do a couple things with it. The first thing I'm going to do is just plot it, right? That's going to take a few minutes, maybe 30 minutes. I'm not really sure. I just want to get a nice animation of everything working and create a very simple plotting script. We're going to have to make it more complicated after that. Then after that, I want to do some algorithm archive work, mainly focusing on the Metropolis chapter like we did yesterday, just reading through it, making sure it's all cohesive and makes sense. Metropolis. And then after that, I want to go back to the n-body simulator, and we're either going to focus on parallelization or better plotting scripts. And for this, I'm not sure what the best direction is. It kind of depends on how one goes and all this kind of stuff. But we're going to keep working on that today. The hope is by the end of the day, if we don't have a parallelized n-body simulator, at the very least, we have something that can create pretty results. And we'll talk about why things are kind of going in this direction in a bit. Now, I mentioned kind of earlier in stream, I'm not sure if this was in the muted part or not, but I mentioned that yesterday I was particularly focused in creating the world's fastest n-body simulator for these types of simulations. And I'm not entirely sure if that's a worthy goal anymore. So looking at the papers that we were looking at yesterday, look, we can definitely beat the papers from 5 years ago, right? We can probably beat the papers from 2 years ago. I guess my overall question is, what purpose does that serve in the overall research objectives that I have? And if I'm honest, it doesn't really matter too much to me. So I'm wondering if we should be focusing on something else. So I'll talk about what the grand scheme of the research is and where we're going and all that kind of stuff. Just fill in the Google form. I'm pre-final year computer science engineering student. If I can be of help in some projects, I'll be very grateful. Yeah, so as far as like working on different projects and stuff, this is also something else. So let's talk about both of those in kind of the same breath. The first thing is, we started this discussion a long time ago. Years ago, we started this discussion with fractal compression. And actually it started before that with the fractal flame method. So let me just kind of put all these down and just see what we got. So fractal flame, fractal compression, and then from fractal compression, we kind of took a detour and we started talking about ASCII art. And I'll describe how this is related. And then we talked about photomosaics. And then finally, somehow, it just out of nowhere, I started talking about galaxy simulators. All right, let me be very clear about what all of these have in common and why it's all basically the same research thrust. So the idea with the fractal flame algorithm is that we take some n-dimensional field, image or something like that, and we compress it down into something called an iterated function system, which is basically a representation of a 2D object in a set of mathematical equations. And so essentially what this does is it allows for us to create a compressed image. Or a compressed field. What I was hoping to do is use the fractal flame method to basically compress any field. And the nice thing about the fractal flame method is that, I'm sorry, I messed up. I combined the fractal flame and fractal compression. Let me fix this. Fractal compression is the act of taking any image and turning it into a 2D field. The fractal flame is the act of essentially taking any equation set and turning it into the 2D field. So one is the compression, the other is the expansion step. Whatever the expansion, I can't remember what the compression and expansion, right? Whatever that other step is. So one compresses it, the other expands it in and out of the equation. So they're kind of two sides of the same coin. What I was hoping to do is kind of compress a physical field. And one nice feature of all of the fractal flame equations that we can use is that they all are technically affine. So if we see like a movement of one particle in space over to this movement over here, there's a smooth linear motion, not linear, there's a smooth motion from one point to the next. And so for simulating like fluid flow and stuff like this, you could probably do it on a fractally compressed grid. So that's kind of where my research ambitions are. However, in order to better understand the fractal compression method, I wanted to take a step back and work on something else that allows for me to do something called shape matching. The idea is that you take like a warped circle and then another circle and you ask, are these the same shape? And so by doing this type of shape matching, I can get a better understanding of how those affine maps work, which are necessary, like I said before, for the physics motion. So what's a good system that allows for me to work with that? Well, that's ASCII art, because you have these situations where you have like circles and your question is, how exactly do we map that onto a series of ASCII graphics, ASCII glyphs? And so that's where that comes in. And then from there, I was like, well, if we're going to do ASCII art, we really should also focus on photomosaics, which is the act of basically turning any image into a set of other images. It's like a face made of other faces or something like that. And then from there, I realized, oh, to do this, we need an efficient histogramming method, which is going to help everything else. And as we were thinking about histogramming methods, I realized, oh, actually, one ideal way to do this is to focus on Octrees and N-body simulators so we can use the histogramming in an actual simulation. So then that's how it's all related, right? And everything here kind of blends together really nicely. It's going to be a full year before all the research is done, but it tells a very nice, cohesive story that I really like. So with that said, that's kind of the whole research ambitions for the next year. As far as asking for help and seeing if other people can help me along with the process, this is kind of part of the hope of this upcoming year. I'm going to try to figure out ways in which we can basically collaborate more with the community. If there's people who come in who have particular knowledge in computer graphics, computational physics, whatever area they're interested in, if this research sounds interesting to them and they want to take part, then hopefully they can. I mean, we're looking at potentially 4 papers that could be published by the end of the year, and this could help you get your name on one of them, maybe. And so this is kind of where we're at. I'm not sure how that community interaction is going to go, but I'm very interested to see how it could go in the future. That's kind of where I'm at. Okay, so with that said, we're actually just going to go right back to the N-body simulator here, and we're just going to plot some of the stuff that we got yesterday with, GNU plot and see what we can do. Yeah, that's where we're at. Name or handle on paper. It would be the name, your actual name. I would not put your handle on the authorship of a paper. The hope would be that, you're part of an academic institution, and that this is actually going to help your career in some way, shape, or form, right? Like, that's the hope. And hopefully, like, if everything goes super well and things are working like phenomenally well, by the end of this year, we can have this open research lab that I've been like dreaming of since I was in high school, But I don't know how possible that is to do in a year. My hope by the end of the year is just to find a way to have a sustainable model of research in an open way. If it isn't able to fund myself, that's kind of okay. I can just return back to academia for a bit, try to find myself a postdoc, and then become a professor, and then slowly but surely start to incorporate these open elements into my actual lab. But if I can become financially stable, this also indicates that I could probably start applying for grants and things like this. And eventually we could start hiring some people to do the research, and maybe getting more than one host on stream or something like this. So we could, I don't know, I've got a bunch of ideas, like a whole bunch of ideas, and we'll just see what pans out and what doesn't. Anyway, with all that said, I think we can just go ahead and hop right into the N-body simulator and just start getting some plots out. It's not going to be particularly pretty plots. It's just plots, something that doesn't look awful. So we're going to do CD, projects, and then Galilee. Okay, I have to Google something. I'm so sorry. Galilee. What is Galilee? It's somewhere that I've read like all the time. Galilee is a region in northern Israel. Is this where Jesus was born? What does this have to do? I know it's in the Bible somewhere. Jesus and the miraculous catch of fish in the Sea of Galilee. That's where I know it's from. Know it from the Sea of Galilee. Okay. Like every time I say Galilee, I'm like, I know I meant it with Lily in the name. I was like, Lily. But now I realize it's like the same as Galilee, which is like obviously a place that you hear all the time in the Bible. So anyway, I was trying to figure out where it was from. Every time I say it out loud, I'm like, I know this is from the Bible, but I don't remember like what story I heard it from. Turns out it's the fish and bread story. Hey, Trash Talk, how are you? Okay, so let's go over here. We're going to CD into projects. Galilee as well over here, ls. And we have our, I'm going to go ahead and make directory, and we're going to call it aux. CD into aux. Okay, and over here we're going to do Julia -- project. Okay, I'm going to do a quick couple of tests here. We have accelerations.dat, so let's go ahead and remove accelerations.dat. And let's just run some stuff. So using revise, and then we're going to do using Galilee. He lived there? Oh, did he live there as well? Man, look, I used to be such a Bible nerd. Like, I genuinely knew everything about the Bible when I was younger. But now it's just like I've forgotten everything, like genuinely speaking. Would we need to be in academia? I've been out of academia for a while, but always wanted to be part of a paper. You don't necessarily need to be part of academia. No. What I was hoping was that this would be useful for people. Like, that's what I was hoping. And whatever that means, it doesn't matter. Like, useful is such an arbitrary term. Some people might be like, oh, this is particularly useful as in it's interesting. Other people are like, this is useful because it's academically rigorous and useful for my research topics, I'm really trying to figure out how can we do research in a way that is like accessible, open, engaging, all this kind of stuff. That's the point of the Laos Labs project. If it works out, great. I'm happy. If it doesn't work out, I mean, look, I'm gonna be sad, but like, I can still probably find my way in academia. Like, as long as I get a few papers out this year, which it's looking like I will, I don't think I'm gonna be struggling too much to, find like an academic position after this is done. I don't think I'll be struggling too much. But the main thing is that this year I'm hoping to paint my CV in a direction that I actually kind of want to work in. So, I mentioned this before, but after I finished the PhD, I was very burnt out of physics. And then after working at MIT again, Galilee. After working at MIT, I was even more burnt out of physics. And so I'm really looking for something that allows for me to, take the computational science knowledge that I already know and transition into an area where I'm actually doing stuff that I find somewhat enjoyable. And for me, that's more computational. Like, maybe it's in the area of computer graphics, which I've been finding really enjoyable recently. But it could just be in a bunch of other areas, like maybe it's in like algorithm development and stuff. Although admittedly, to be fair, like I think I want something a bit more applied than like straight up algorithm work. The problem with algorithms is, as much as I love them, a lot of the theory is very theoretical. And like, you could, for example, have an implementation of, I guess here's the thing. I care more about benchmarks and big O notation. That's the thing that I care about. So if I have like, if I have the ability to do complexity notation, that's fine. But if I could do a benchmark, that's even better. That's kind of where I'm at. Okay, let me do a quick ls here, ls back directory. We should have check.dat. We also have accelerations.dat. I don't know why we're outputting accelerations, but that's okay. So let me do GNU plot in here. And what I'm going to do is I'm just going to plot /check.dat. Sure. Let me do I0. And then we're going to do I1 with a replot. Yeah, I see what's happening. I2. Okay. I3. Right. Okay, so this is why I wanted to make sure that we had some sort of animation. So I'm going to create a quick GNU plot script just to animate all of the time steps. This isn't going to be like a beautiful script or anything. It's just going to be something that allows for me to just write stuff out. And so we can like watch an animation of this unfold. Okay, let's go ahead and get it done. So we're going to do vi plot.gp. Again, it's not going to be like the most beautiful script. We're going to have to like update it every time we want to do a new plot, but that's okay. Set terminal PNG Cairo. Misspelled Cairo. Okay. So the simplest thing that we can do is there's like a for loop that I can do in GNU plot. Let me think. So set size square. I like square plots. Let's see. I'm going to want to do, I think we can just do for I equals 1 to 10. I think it's like 0 to 10 or something. We're going to have to modify that. I really don't remember the notation here. And let's go in here. So we're going to do GNU plot for loop. I misspelled loop, but yeah, I should know what I mean. It does not know what I mean. Try it again. Loop structure inside GNU plot. Here it is, for data.i.text using perfect. Okay. That's exactly what I was looking for. So we have a plot for, but I don't necessarily want plot for. I just want an overall for loop because we're going to have to change the output file name every time. So we're going to have to do like set output, something like set output. We'll say, oh man, I've done this before. Where did I do this before? I've done this multiple times before, where I like output a bunch of files. Let me check. Go over here, Control C, CD projects, Simuleo. It's probably Fractal, ls here. Let me see, what do we have here? There should be like a plot.gp or something, ls star.gp. There's a plot Barnsley tree, vi plot Barnsley tree.gp. So it's for t is equal to 0 to 100. We plot for index Barnsley tree.dat. Then we pause 1. Okay, so this just plots them all. But it seems to be the notation. It seems to be what I'm looking for. Something like this. So we plot Barnsley tree.dat I index. Okay, I see what's happening. Thank you so much for the bits, Anonymous Cheer. I appreciate that. Speaking of which, I'm wondering if I should move that down a little bit. This thing's like all right up here at the top. Maybe I should move it a little bit down, something like that. No one saw what I did, but that's okay. It's totally fine. So something like this should be fine. So it's a do for. Where are we? We are vi plot.gp here. So it's going to be do for, and then it's going to be open this, close there, set output. Do I have to do like a, I think I can just do the following. I think I can do out. Oh, right. I needed a zero pad. That was the issue. How do I zero pad? Well, let's do index dot PNG or something. I'm working on it. 1 second. Something like this, maybe. And then we want to actually do the plotting, which should be straightforward. It's just going to be plot whatever the data file is. So // check .png. Sorry, .dat. And then we're going to do index ind here. Modify this up here. Every now and again, I still do a lot of fiction writing, but not nearly as much as I used to. Man, I actually thought about this recently. Here, let me finish writing this line. I index point size 2, point type 7. Okay, so I thought about this recently. Did you finish Grimm? No, I didn't ever finish Grimm. So for those of you guys who may not know, we used to do a Writing Wednesday here on stream. And the truth is, I used to write a lot of fiction. Like every day I was writing another short story. Some of them were good, some of them were not so good. I mean, that's just the nature of doing writing, you know? Like if you're trying to get better, you just got to write a lot of stuff, and sometimes it works out, sometimes it doesn't. I quite liked the stuff I was writing, and I do want to write more. But I don't know, I couldn't figure out how to get it to work, you know? And so like, I kind of decided at the start of this year, well, not, at this point in this year, I decided that I'm going to have to pick one. between the research and the fiction writing, and so I unfortunately am not doing that much fiction writing. I do very much enjoy reading papers and stuff. Like I very much enjoy this, what I'm currently doing. But part of me was trying to figure out a way in which I could incorporate the storytelling into the research work that I was doing, which is part of why I was like so interested in doing like the computer graphics approach. Because if I do start doing research in computer graphics, I could do the Pixar approach, which is to say I tell a good story using the tools in which I've developed with my computer graphics research. You know, so it's like, hey, maybe we use color quantization or something, or for example, we could use I was thinking about using a photomosaic algorithm or something to tell one of the stories that I had written a while ago about like this person whose memories were flashing before their eyes and they kind of saw all of them telling one great story all together. Having a photomosaic algorithm kind of tie all that together would be a very interesting way in order to tell that story. You know, like I could imagine like interweaving all of it together. And so, you know, the way in which I do research is very much motivated by the way in which I want to tell stories, but also it's the other way around. The research itself is motivating the stories that I'm telling. And so I could imagine, you know, publishing papers as well as, you know, making these short stories available on YouTube. And more than just writing them, I could like, you know, animate them, and I could, you know, like really tell these amazing things. And I really want to try that at some point. Maybe once I get like, I don't know, I just don't know how to get there. But maybe the actual answer here is maybe I just keep going with research a bit longer and see if I can use that research to tell stories. Like maybe that's what I need to do, and that's the direction I need to go in. Yeah, I'm not entirely sure. Yeah, I'm gonna be right back. Give me 1 minute, and then we'll keep writing this plotting script. I'm so sorry. I'll be right back. Yep, sorry about that. I had to run upstairs really quick. Did you finish Graham? Printf at sprint. Yeah, I should be using that. I just suck at using at printf because I always forget how to actually use it. Browserify.org used to have a daily comic section, which was cool. Let me take a look at that. I didn't actually know what that was. Output equals... Ah, perfect. That's what I want. Something like this. Perfect. Yeah, there you go. See, this is why I stream. People just tell me what I'm supposed to do. If I sit here for long enough and ramble, someone in chat will be like, oh, I absolutely hate this guy rambling so much, and will give me the actual solution. It's happened more than once where like I'm in the middle of a ramble session, then someone in chat's like, oh, you should do this. I'm like, oh, thank you. This might not be, I think the @sprintf might be something that's like maybe Julia-esque, but we'll see. Looks finished to me. What do we have here? I recently found a good work pattern. Wait, I missed something. Grim was really grim, but I like it. Output is equal to @sprintf. I recently found a good work pattern. I post a chapter weekly online of the story I don't like so much anymore and procrastinate the rest of the week writing something I like better. That's totally fair. Okay, so Though I haven't tested it, I don't have Julia. Oh, interesting. Okay, let's figure this out. Let me ramble for just a little bit. I'm so sorry. So the story that people are talking about in particular was one I put on GitHub. It's called Grimm. It's specifically Grimm's memoir. Um, oh man, I love this story so much. It look, I've written better things than Grimm. But this is the one that I kind of keep going back to because there's something about it that I kind of like the story. So the idea is that you've got this guy who is a synesthete, but he was told he has prosopagnosia, I think is what it is, which is the inability to see faces. And so the idea is that this guy is actually able to see what he perceives as a person's like soul in front of him. So he'll see like, a person, and if he doesn't really understand who they are, he only sees like a gray haze over their face or something like that. And the idea is, the closer, as a person gets closer and closer to death, like their haze or whatever that is over their head starts dwindling more and more, right? So the story is the story of this guy, how he became a coffin salesman, and is super good at his work, but has like a deep love for other things, but doesn't know how to express it because he doesn't understand human emotion. And so it's kind of like from that story. In particular, what I love about this story is that like I invented this character whose name was Jackie. I don't know why I called her Jackie, but like she was like so full of life, and it was just like this dichotomy in a way between this one guy who doesn't understand human emotion and this girl who's like so incredibly full of life. She's just like a rainbow before him, and so it's like this crazy like back and forth that I really really liked between it. Now the writing here could have been a lot better. The problem was I was writing it as Grimm, and so Grimm's character is kind of like just weird, and so the writing was reflecting his like odd, erratic behavior that doesn't really make sense because he doesn't understand how to make it make sense. And so I don't know, like I loved writing this story so much, and I really think it's a good story, but I don't know how to like make it work, like I don't know how to like. I had it all planned out. I know where it's supposed to start. I know where it's supposed to end. I just don't know how to tell it cohesively with with what I have now, like with the Open Research Company. How does that all have to do with creative writing? It doesn't. It's kind of hard to make it all work together. And so I ended up being like, well, if I'm going to make something work, I'm going to make something work. And the thing I want most right now is the Open Research Company. Because I kind of have the naive feeling that, again, if I work on the computer graphics of it, maybe I could tell these short stories on YouTube or something. I could find a way to tell these stories in a way that are engaging to a large group of people. I don't know. This is where I'm at. Anyway, so the story here, feel free to read it. I mean, the post was up here by 10x Programmer. The intro is way grimmer than the actual story if you go into it. But yeah, I don't know. I had a lot of stories like that. In fact, if you go to, I think it's scribbleaos.com. It might still be up. Yeah. Good old scribbleaos.com. I was posting here like somewhat daily sometimes. Like here's January 2021, January and February, like lots of stuff from that. All of December, I posted a lot of stuff. My favorite one last December was how elves are made. Oh, this is my favorite one. It's so dark. Anyway, that's what it is. Like I don't know. Like I used to be super into it. I used to write every day. I still love writing, and I don't know, like if I could manage the time, I'd love to like publish books and do the research. I don't know. I don't know how to make it all work, That's the problem. I don't know how to make it all work. Arbitrary deadlines and useful procrastination make for decent productivity. Yeah, like maybe that's what I should do. Like it's not like I'm wasting too much time. It's just now all the time I used to do for writing has turned into paper reading. And I don't know, maybe we should do another Writing Wednesday. Like spending a day a week on this doesn't sound like a bad idea. I love doing it. Who knows? Maybe we'll get an audience for it. I think the big problem with Writing Wednesdays was that like what I was doing was I was just kind of reading out the stories as we were getting through them. And the problem with the stories was that like, I wrote them. If I was reading something someone else wrote, I would probably do it at a much slower pace. But because I was reading them, I was kind of like I was nervous about it. And so I was just, talking and reading through it quite quickly. And I didn't find a good pacing for it. But maybe I kind of want to do it again though. Like somewhere I kind of want to do it again. Anyway, This is completely rambling. Let's get the plotting done. Let's get our galaxy simulation done. We'll do a bit of rambling after that's done. Maybe talk more about doing more Writing Wednesdays. We'll see. BattleMe10, thank you so much for following. Really appreciate it. So let's get our galaxy plotted. And yeah, see what happens. Is this actually going to work? I don't think so, but let's try it. GNU plot.gp. sprintf is not a string variable, unexpected or recognized at index. Right, okay. Maybe get Microsoft Sam on the narration. Who's Microsoft Sam? Oh, now I did think about... Okay, wait. I don't know who that is, but I assume it's like someone to voice particular characters. Like you can like make your computer say something from the terminal. I thought about actually doing something like that. Is GNU plot not Julia? Yeah, it's GNU plot. I forgot the sprint whatever. Sprint Sprite Blast. What is Sprite Blast? When you tab and don't even know like what commands you have on your computer, that you need to clean your computer when you start seeing that. Okay, what am I going to do here? sprintf GNU plot. Let's do here plot line. Sure. GNU plot tricks. This probably. Where are we? No. I specifically wanted at sprintf. Let's go here, there, and let's see. GNU plot surprising. GNU plot. Oh, somehow I misspelled GNU plot. Perfect. Using at sprintf. What do we have here? At printf. So we should be able to do the following. Here, where is it? Here it is. So it should be sprintf, and then we should be able to do something like this. Oops, messed that up. This, and then maybe put a comma there. See what that does. Oh, wonderful. We got it working. What happened? Did it just like plot it to my terminal? Okay, well, perfect. It's all ship it. We got it working, definitely. Oh my gosh. Okay. Okay. What happened? L is here. Well, we don't have any output files. Shoot. Clear. Reset. Okay, well that didn't work. But we were getting somewhere. Okay, so we have the output equals this. And then we plot. And oh, that's because I need to set output. I think that's what I need to do. All right, let me try it one more time. Okay, ls here. We have a bunch of output files. So let me just do Mirage out 00.png. Okay, well we have something. I'm not sure it's what we want, but we have something. So here's what I'm going to do. I'm going to go into plot.gp. I'm going to do no label, set label. What do we do? Set label. I don't want to freaking. What is it? How do I remove the maybe set title? This? Write this, and I think this has to go to 9 instead of 10. All right, let's try it one more time. GNU plot.gp. Unexpected set. Wait, what do you mean? Unexpected. Oh, it's supposed to be with title. Try it one more time with GNU plot. Unrecognized plot type. Oh, there's no... It's just title. I keep forgetting how to use GNU plot. One more time. Perfect. L is here. Now let's do Mirage. Okay, so there's no... Okay, so we should be able to run a longer simulation now. Yeah, okay. Let's see what happens if we run a longer simulation. So we're going to run it with 100 particles for 10 time steps. Now we're going to go over here and we're going to do the same thing. Oh, I need to remove a file. Remove check.dat. Okay, try it one more time. Run. Now we're going to try plotting it. Mirage. We have 100 particles. Now, they are not really moving in the way I thought they would, but this is fine. So I know what's happening here. The problem is we have all the particles so close together, and they're basically being like forced apart because of the force law that we're using here. So we do have something that's plotting, so that's good. What I want to do is create a very quick animation, and what I'm hoping to do is just see a bunch of particles from very far out just come together, whoosh, and then it's kind of spread out. This is what I'm looking for, something like this. What? Oh, wow. It's like some sort of interpretive dance. All right, let's keep going. What am I going to do with my life? I need to do something, and I totally forgot what it was that I was going to do, but I just said it, so let's just keep going. I'm going to go into VI source, simulate, and what can I read in? So I can read in the integrator, but what I want to be able to read in is the initialization checks here. So let's go here, there, and what I want to look at is source and then initialize. Okay, so I need to read in grid extents. So let's go into simulate. There we go. And we're going to read in grid extents here. I hate this call so much. Grid extent equals 1. Grid extents equals 1. Extents equals 1. Okay, so now what I want to do is I want to run this again, but I want to specify that the grid extents is equal to 1,000 or something. Oh. Oh, it's pre-compiling. Right. That's what happened. Okay, so now let's try plotting it one more time. CD aux, and now we're going to run GNU plot. Let me run Mirage. Oh, that's obviously I have to remove check.dat. Try running it one more time. Now we're going to run GNU plot, run Mirage. Okay. 1 second. What did I write? Let's do, I must have did this wrong. VI back into source and then simulate. Yes, that's what I meant. Thank you. Oh, that's unfortunate. I'll move the optional arguments down to the next line. Yank, paste, $. Okay, let's try running that one more time. Hopefully we get something a little bit better. Remove check.dat, galilei.run. Okay, we have all the particles, and it's kind of difficult to see what's happening here. But it looks like... Okay, what is happening here? So they are being... All right, let me set the X and Y bounds. Let's go into vi plot.gp, and we're going to do set X range -1,000. I think this is it, 1,000. And set Y range as well. GNU plot. Mirage. Okay, so here we have, I see what's happening. Okay, so we do have the particles doing things, but they're not doing exactly what I thought they would do. Cool. Okay, so let's see, what do I want to do? I could make it more physical. I could make it more physical. I could let it run for longer, because then the particles should come back. Let me also change how we're plotting this as well. So let's go into VI, back into simulate, source and simulate here. And with the output method, we're going to do D4D. We're actually going to output at the start of the iteration instead of afterwards. And I'm going to remove the acceleration files for now. Okay, write and quit. Over here, we're going to remove check.dat, run it one more time, and now we're going to plot it again. Run Mirage. Okay, so here's what's happening. We have all the particles together in this box, and the very next time step, they go whoosh, way out far. I'm going to decrease the time step and increase the number of points here. So I'm going to 0.001, and 1000. Okay, now I'm going to remove the data file because I'm an idiot and run it one more time. Okay. Yes, I need to change the gravity so it's not like super bad. Stardo, thank you so much for following. Really appreciate it. Okay, so next thing I'm going to do is run vi plot.gp, and then we'll start making this more physical. This is going to go to 999. Now let's run. Can you plot? I don't know how long this is going to take. Actually, this is a bad idea. I should probably have timed this. Let me also open up htop while we're at it. Oh, okay. Worked. Okay, let's do Mirage. Okay, so we have all these particles here, and they are new. Okay, wait. They immediately spread out. It's not even like they're just 1, 2. We didn't need any of the other 999 frames. They're all just like, I mean, do they even come back is the question. Is there a single frame in here where we'll see any particles again? I don't know. The force was just too great. They immediately spread out. I think I said thanks for following Stardo. I don't remember if I did or did not, but I appreciate it. I don't think they're going to come back. I really don't. I think we're stuck. Wait, I'm still going though. I still have hope. I still have hope. We still have 100 more frames. And no, they didn't come back. Okay. They were too far gone. Okay. So, we can do two things. One, we can try to add physical units to this by adding the actual gravitational constant. Or we can fudge it a bit more. Let's fudge it a bit more. Thanks for the chair. Let's go ahead and remove this. And we're going to make the box really, really big. Run it one more time. Go to vi plot.gp. Modify these guys so they are from... This isn't the ideal way to do this. There's a much better way. Okay, so now we're going to run GNU plot. Give it a second to do its thing. And then hopefully we have something that's a bit better. So I had the particles like way further out this time. So this should mean that the force pushing them... so what's happening is these guys are... Like you have a single particle that is affected by 1,000 other particles. Let's just do some back of the envelope calculations after this is done. So here we have all of them. Right. Okay. Well, this is prettier. I'm not entirely sure. Oh, I think, did I not remove the previous check.dat? What happened? Oh, actually, now I'm quite interested. Do we ever... I think I see what happened. I increased the number of particles. I did not increase... What did I do? Wait a minute. What did I output here? There's 100 particles. I increased the number of time steps is what I did. I wanted to increase the grid extents. Okay, let's go ahead and remove check.dat. Run this one more time. And now we're going to try plotting that again. Give it a second to do its thing, and hopefully we get something that doesn't look awful. I hope everyone's having a great day, by the way. Obviously, there are much better ways to do this. It's just kind of a quick back-of-the-envelope type of thing. So we have these guys. Give it a second to load all the images. Okay, I think we're still running into the same problem. I probably should just FFmpeg this all into a video instead of looking through the images in this way. So here we have all the points. And then that's it. I don't think they're ever going to come back. I think they're gone. It's okay. All right, let's do some quick back-to-the-envelope calculations, shall we? We're going to go over here. So right now, journal, new page before, the force is going to be equal to 1 over r squared. That's literally all I put in. In principle, it should be equal to gmm over r squared. So let's think about what we're doing here. Did you forget the minus in the gravity calculation? Yeah, I did. Yeah, I think you're right. Let me try this one more time. I was like, it's 1 over r squared. So the reason I think I did that is because I was so used to doing dusty plasma simulations, which is what I'm used to when I think about MD. And they have they're repulsive, not attractive. And so because of that, I think I just wasn't thinking. Let's go to VI source, and now we're going to go into Where did I put it? Forces, maybe? There should be just gravity, and we're just going to return a negative. Here I am with a physics PhD, but I don't remember how gravity works. Oh, man. It's one of those things, you know? Okay, once we get a kind of neat animation coming from this, let's do Mirage. Okay, what's going on? Give it a second. It just has to load all the images in. And then we should be able to... Okay. It's still doing the same thing. And I'm wondering if this is because... Our time step's quite small, though. Let me just turn Julia back off and on again. It might not have like pre-compiled that appropriately. Let me do using Galilee. Give it a second to do all the pre-compilation steps. And then we're going to run it one more time. Let me also check to make sure I actually wrote the file correctly. It is now negative. Good. And now what do I want to do? I want to remove the appropriate data file. And now we're going to run Galilee.run. Give it a second. It's still pre-compiling. And now we're going to do GNU plot. And then hopefully we get some nice images out. Probably I should just FFmpeg it all into a single video. I'll do that in a bit. Right now, I kind of like the ability to like scroll through images. So even if it takes an extra second to do this type of stuff, I'm happy with that. So here's our initial distribution of points. And dang it. Yeah, it's still doing... Let me just zoom out really quick. Let's do... Where is it? Let me zoom out like a couple order of magnitude. Okay, so with that said, let me think about this. I think the forces are just super high, I think is the problem here. And the time step's too small to capture the actual dynamics. So let me actually calculate the forces happening on any given particle, and then let's work on that. So Mirage here, so here's all the particles at the start, and oh my gosh, there they go, they're spreading out. At least this is something. Okay, what I'm going to do is I'm going to turn this into a video to have playing in the upper corner, so we have something that's playing, and you know, so I'd like to have something visual on screen for people to look at when we get to that stage. So we are seeing the particles like moving out, like look, something's happening. It's not particularly beautiful looking, but hey, that's okay. So what am I going to do next? I'm actually going to, what is it, Mogrify invert? Mogrify invert star.png. Turn inverting. I forgot how to do this. I was going to change it just to black so it fits the theme a bit better. Negate is what I was looking for. So I should be able to do negate star.png. Should happen. Give it a second to do its thing. I don't remember if this takes a while or not, but basically I'm just turning all of the images so they're black and white. Can you increase gravity to see if it would slow down the spread? Yeah, I was going to check that in just a second. I want to see what we want to do to the gravitational constant to do that. Exactly. And so I was going to do a quick back of the envelope calculation. So now we should have all black images. Perfect. And the next thing I want to do is just put that all into, so I'm going to do FFmpeg. Oh, how do I do palette generation? And then we want to do converting images into video, FFmpeg. I always forget how to do this every single time. So I'm going to create a function in here that's just going to be create video. Video.sh, I guess. And we're just going to put the FFmpeg commands in here. I need to create a palette first. Sure, RF image. Do you have 1 over R potentials or 1 over -1? So I just put -1 over R squared. Should be a potential? No, I don't put the potential in. I put the force directly in because we're looking for the acceleration. So we're solving essentially f equals ma. It's just rather a is equal to f over m. 1 second, let me quickly create this video, and then we'll go from there. So ffmpeg, this is the one I think I'm looking for, or something like this. Wait, where are we? Add MP3. Where is it? Using ffmpeg to convert. Oh, here it is. This is exactly what I want. Perfect. There we go. Go over here, and we're going to paste this there. So we want rate of 60. Maybe that makes sense. I don't know what f of image 2 is exactly, but this is going to be out. I think 4.png is fine. This maybe? Maybe? Yeah, let's just see what this does. So we're going to do chmod plus x create video .sh /create video. Okay, L is here. We should have a test.mp4, mpv test.mp4. That is indeed a video. So the only thing I want to do now is create a palette so that it just does it more effectively. So we'll create the palette, use the palette, and then we'll have something play in the upper left-hand corner for people to look at, so we can see the most recent simulation. And this is just something I can just show up there and just have on repeat, so I don't have to think about it. What am I going to do next? So I'm going to create the palette. So how do I do that? 7. 1 second. You forgot the shebang line? I mean, I can add that in. It's fine. Palette generation, ffmpeg. I basically never put that in there. I probably should. Generate color palette for ffmpeg. This should probably give it to me. Let's see. ffmpeg target.png. Sure. Okay. So I think I can just do the following. Let's go into vi create video here. Paste that. I think we're going to look for this guy here. And I believe that'll create the palette. Okay, so that should create the palette. And then how do we use the palette? We use it by, okay, thank you, Stack Overflow. Try this again. Here, maybe. What do we have? ffmpeg palette gen palette. And to use it, we need to do, we just need to add it as an input palette.png as well. Okay, perfect. So if we just do -i for palette.png, in principle, this should work, I guess. Okay, let's see what happens if we just do /create video. Sure. Okay, now we're going to do the last MPV. I'm not convinced it's any better than what it was a second ago, but we do have a visualization. So let's just have that visual. What I think I might do, whatever, I'll leave the FPS. Who cares? No one, I mean, genuinely, who cares? Okay, so let's just go here. Let's do CD. Okay, what is the bin bash line? Shebang line. What is that line? I always forget what it is. Bash script initial line. I always forget what the actual line is, which is why I never put it in. Bin bash. All right, thanks. I'll put that in there. Vi create. All right, just for you, Yane. Okay, right and quit. Go over here. CD projects, Galilee, Ellis here, and now we're gonna do CD aux, MPV, loop 0, test.mp4. Is this not gonna loop? Oh, it does loop. Perfect. All right, kind of crappy visualization, but it's just what we have for now. So let's just move this up here. There we go. Move this down. There we go. That's our visualization for now. We'll work on it in a bit. Ooh, look at this. Oh no. Let's move it down here. My GPU is struggling a bit. Oh man. All right, move this down here. Is that going to be all? Is that everything now? Let me see. I'm going to open up a new one. Yeah, everything is slow now. Oh, is it just because of MPV? Is that what's happening here? Oh well. It's probably fine. As long as I don't have to move anything around, it's fine. Okay, whatever. We have something that's like visualizing in the upper corner. So I want to do a very quick back of the envelope calculation. In fact, let me just have this here, there. Perfect. The stream is laggy now, is it? Oh yeah, definitely. Oh yeah, 100%. Let me fix that. So that should have at least fixed my my video audio desync. So you're telling me if I move this around a bit? Oh yeah, I can definitely, my stream is definitely lagging when I'm doing this. Okay, I didn't realize I used all of my, okay, I didn't realize I used all of my compute power on my computer moving that around. That is something to know for later. Maybe I should switch Windows managers actually. And your audio is off. My audio looks like it's still on. Okay, well that's good to know for the future. Is this any time I play a video now that this is going to happen? It might be because I have two monitors now. What size are the images? They're not particularly big. The resolution should be, yeah, so I have to change, I know how to synchronize it now, which is great. How do I check the size of the image? What? I'm in the wrong directory. They're 20 kilobytes. It is 640 by 480. So it's not particularly big. The test.mp4 file is only 368 kilobytes. So anyway, it's something to keep in mind. I'll just keep watching it. You guys just let me know if there's like some video and audio desync to worry about. Okay, back to the envelope calculation. Negative, GMM over R squared. So it might be the loop functionality that's getting it. That might be the actual problem here. But I have no idea. Okay, so force is GMM over R squared. So we have particles all around here, right? So we have roughly, 1,000 particles, we'll say. So this means that if you have a particle here, and you have a box size of 1,000 or something like this, you have 1 over R squared. So my gut feeling here is that the particles are so close that you get a very, very large force, because right now, I'm just doing negative 1 over R squared. So if you have particles that are less than 1, like they're close to each other, and this radial distance is under 1, then your force can be quite high. But otherwise, the force shouldn't be too big. That's weird, actually. The force shouldn't actually be that big. Maybe I should just let the simulation run for longer, actually. Let me do the same visualization I just did, but with a much longer time step. Yeah, let me try this again. Okay, so we have a much larger time step now. And let me just try running a new plot over here. I guess we can make another visualization. Hey, Shudipto, looks like you're already modeling the expansion of the universe. We're modeling something, not necessarily the expansion of the universe. We're just getting something done. Yeah, I don't know. It's not going as well as I would like, but we'll get there. So the next thing I want to do is just mirage. So here we have all the particles. They should initially expand out, but they should hopefully come back together at some stage. Please? Just come on. Please come back together. They're still going out. They're definitely not coming back together again. Let me increase the time step one more time. Remove, and let's just do a time step of 10. Sure, that'll do. Run GNU plot one more time. And hopefully, like our time steps are quite large now. So this is not going to be particularly physical, but I'm just trying to get something, I think what's happening is they're all just zooming past each other, and then they're going to come back, I think. Are you giving them some outward initial velocity? I'm not. No. No, I'm not. Which is, yeah, I agree. It is weird that they're all... Yeah, I don't know why they're all going outward. I thought they were zooming right past each other, but actually looking at the visualization again, they seem to just be going out. They don't seem to be coming... What? Okay, you're right. I'm a bit confused here. Hey, Kiozis, how are you? Okay, let me take a look at the force again, the force of gravity that we're working with here. Yeah, but clearly these guys are not coming back together. Okay, perfect. I'm going to do this, and then let's go into VI source. I'm doing okay, thanks for asking. Let's go into forces.jl. So our force of gravity is negative, position 1 minus position 2, a negative 1 over r squared. That's all it is. So could be a sign on the force? Yeah, so I mean, it should be a negative, right? Am I wrong? We just changed that to negative because we thought I mean, I could change it back to positive, but we literally just tried positive and negative. But I agree with you guys that it looks like a sign error because like initially when someone said, is it negative? I'm like, oh, of course. Timescale way too small. Yeah, so that's why I tried increasing the time steps as well, because I thought if the time scale was bigger, then we would be able to see the visualization better. This is impressive. Yeah, so for the record, I didn't answer your question before about what we're doing. I'll go ahead and update everyone on what we are doing. So I'm Dr. James Schloss. I run a number of different things, including the Arcane Algorithm Archive, a YouTube channel, and a Twitch stream, both called Laos Labs. What I'm trying to do is basically do open, engaging research with you guys, the community, and my hope is that we can do some cool visualizations. So what we're working on right now are some cool research together. So what we're doing right now is we're working on a 4D galaxy simulation. The overall process or the overall idea is that, you know, if you take a 3D galaxy and you let it move with time, it eventually forms a 2D disk. So here we're seeing what happens in 4D. Does it create two 2D disks because you can double rotate? I don't know, this type of stuff. But I'm actually fundamentally interested in like improving n-body simulation dynamics, working on octree meshes, stuff like that. You're not adding the accelerations. That could be it. Let me do find acceleration is going to be just gravity. You're totally right. You're 100% right about that. My find acceleration function does not work. Thank you. I apologize. That was me writing shoddy code, just trying to get something down written yesterday. Okay. Only listening to YouTube channel. I'm French. Sorry. If I request to repeat, yeah, feel free to ask any questions if you have any. Yeah, you're right. You're completely right. Using the radial force law, but the system is Cartesian. Should still be fine. Wait, that could be another issue. Let me think. So those are two potential issues. So let's work on that. So first is sim type. We do have to add all the forces together because you're totally right. I was not doing that. So we do the sim type, which is going to be the force of gravity on all of the accelerations and all of the positions. The sim type we're reading in is going to be n-body down here. So n-body here is going to do, when we say 4j is length of positions, we say the temporary acceleration is going to be equal to the force law. What we should do is plus equals. So that is definitely one big error that needs to be fixed. Okay, now for the radial thing. Let me think. We're definitely using Cartesian positions, like x, y, z. So r, but we should still be able to do x squared, 1 over r squared. Look, it's been a long time since I did any proper physics. Let me just double check here. So, it doesn't matter. Let's move down a little bit. So it's 1 over r squared. R squared is going to be x squared plus y squared. So if it's 1 over r squared, we have x squared and y squared. Then we find the differences in x's and the differences in y's, and we add them together. So what I'm doing is the differences in x's and y's, and the differences in... Right, so I guess what I need to do then is sum the two. So it'll be 1 over... So we take two positions, and the positions have an x component and a y component in them. And it should just be... Can I do sum here? This isn't going to be the best way to do it, but... Yeah, that makes it kind of messy, doesn't it? Okay. One second, I need to think about this. So we're turning 1 over position 1. Does that actually compute correctly? One second. First, let me go ahead and run this again, just with the updated accelerations. And then the position 1 and position 2 that we're reading in here are positions of I and positions of j. Position is going to have, I think, an xyz component. So it should be just xy. So we should actually be returning 2 different accelerations. Oh, yeah, so we're returning 2 different accelerations, one in the x direction, one in the y direction. Yeah, that's actually what we wanted. Right. Need to multiply by unit vector. Right. Yeah, you guys are right. This is me completely forgetting basic physics. So we want to get out an acceleration in the x and the y direction, right? So that's what we want out. So we have a magnitude and direction. So first we need to find r squared. And then we need to put this into the x hat and y hat directions afterwards. Oh gosh, this is me completely forgetting like literally all basic physics. Like this is stuff from like, you know, literally high school, and I've completely forgotten. This is like just as embarrassing as me forgetting Taylor series expansion type of stuff. Like completely forgotten all of this, you know? Unit length, need to multiply by unit vector. Right. So what we need to do then is we need to find the magnitude of r. So first we need to find r, and then 1 over r squared. That's fine. For 1 over r squared. Now let me see. How do we do the unit vector again? It's like x over the magnitude of r or something. What is the unit vector again? It's like I could just look at my old code because I know it's there, but I kind of want to just not do that for now. It's u over u, but what's u? Use the original vector and use the magnitude of the original vector. This might be a silly question, but what is a good source to learn Julia? R squared is equal to sum in position x. That's kind of gross. The sums there are super gross. Yeah, I'll unroll the sums, but that's fine. Vector divided by vector norm, I think. Right. I think what Shadipto put down is correct. Let me see. What I'm going to do next. Yeah, position 2 minus position 1 over the absolute value of position 2 minus position 1. Yeah, that makes sense. And then what we want to do is multiply that by the 1 over r. So find 1 over r magnitude, multiply by that. Perfect. That's what we need. Thanks. So what am I doing next? There was a question that I'm going to answer really quick, which was where do you learn Julia from? That's a super good question. Unfortunately, I don't have a very good answer for this at all. I learned Julia just through the years while working on like Julia 0.3 up like through the works and everything. So I've just been kind of using Julia and therefore learning Julia. I think the Julia documentation is actually quite, it's not particularly good. So no matter like what you're trying to run or what you're trying to learn, I don't think there are very many good resources there. Now, if you're learning Julia specifically for GPU computation, there is actually a good documentation for that. So if you do Julia GPU here, there. So this is actually really good for learning Julia GPU. I quite like it a lot. Some of the individual docs are actually pretty good. Like, for example, if you're trying to learn how to do, do a particular project or something, but I don't know of any like good books. Or something like that. I don't know Julia, but I like this site to learn languages and it has a Julia track. Sure, maybe that'll work. If I'm totally and completely honest, I don't know the best way to learn Julia as a language. I only know how to learn what I know, which is mainly GPU computing. And for the record, this might not be good advice, but usually when people are trying to like learn a language, the easiest way to learn that language is just to try to do a project in that language. So just pick something that you're interested in and just try to write it out, and just like Google the problems as they come about, that type of thing. I know this isn't super good advice, but that's unfortunately the best I can do because I don't actually know the proper resources. Okay, so let's get this written then. My case does not currently use GPUs right now. That's also totally fair. It's kind of rare that your case will use GPUs. It's just something that I've done. Okay. So let's actually get this done then. Here's what I'm going to do. If position 1 is not equal to position 2, we're then going to say arm is going to be equal to Position 1 minus position 2. We have squared sum. So we should be able to do the following. It should be, we're going to use r squared anyway. So let's do r2 is going to be equal to x squared over y squared. So, sorry, 1 over x squared plus y squared should be what it is. So it should be position 1 of 1 minus position 2 of 1. So that should be the difference there. And then we should be able to square that. So we're going to multiply that by, oh, this isn't going to work, is it? We might actually have to use the sum. I hate using the sum. That's going to be really nasty on GPUs because it's only a 3-element sum. We might be able to do a vector broadcast or something. We could just do the sum. I hate it. Fine. It's going to be nasty on GPUs though. I used to use Project Euler as a source for basic problems to solve. That's also, yeah, a lot of people really recommend that as well. Okay, we'll do it. Sum of position 1 minus position 2. Sorry, 2 minus 1. Okay, this is going to be our r squared, so we should be negative 1 over r2. I'm going to put this in parentheses here, and then we give it a vector direction, which should be position 1 minus position 2 over the absolute value of position 1 minus position 2. So times the unit vector here. I guess I could define u as well. Okay, let's do it. U is equal to position 1, 2 minus position 1 over absolute value of position 2 minus position 1. But it has to be in magnitude, right? Yeah, I can talk about whether the sum sucks on the GPU in just a second. Position 2 or position 1. To be fair, it might be okay if we have each thread do all the sum together. I'll explain what I'm running into in just a second. Should be sum position 2 times position 2. Wait, what? It should be sum of position 2 minus position 1 times position 2 minus position 1, right? Yes, you're correct. You're definitely correct. Sorry about that. Yep, thank you. Yeah. Okay. In general, I'll trust people like, Shadipto or people in chat who like are currently working on this. Like I'm working on like first year in the PhD. This was like second nature. I'd be like, oh, it's super easy. But it's been a long time since I did basic physics. So I'm kind of a bit rough. Okay, the absolute value of position 1 minus position 2. Shouldn't this be a magnitude? It shouldn't be like ab squared or something. In 2D, you need the gradient of the potential to get the force and acceleration, but the potential is symmetric in this case. Wait. In 2D, you need the gradient of the potential to get the force and acceleration. What do you mean? I'm sorry. Are you saying what I'm doing right now is incorrect? What would you say I need to do? Sorry, look, I gotta be honest, like, this is all stuff like, there's a problem with n-body sims. Like, you have to deal with physics, and it's like, I hate doing this. Like, there's always a tedious part, and this is like the tedious part for me, getting the equations right and all that kind of stuff. I know it takes no time at all, but it's like, it's the part that you're kind of like, like for me in particular, it's like, I want to work on like octree gridding. I want to work on this, and I get it. Like, you got to get the basics down first. I get that. But also it's like, you get kind of a bit, yeah, I don't know. I don't know what it is. I get just like, it might be like PTSD from the PhD or something coming back, but like every once in a while, like as I'm doing this, I just kind of like start hyperventilating a bit, being like, oh gosh. MOR squared is the gradient of UR in NAD. I was saying in general, if you diff the V potentials. It's been a long time since I did that. So like, you've got like Lagrangian mechanics with T minus V, L is equal to T minus V. Oh gosh, it's been so long. I don't remember anything, like literally anything from my graduate classes about this. Yeah, completely forgot all of it. Oh my gosh, this is super embarrassing. Like, I did this 4 years ago. 4 years ago, this entire thing, like the octree, the Barnes hot, took me one stream. I did it in 2 hours and done. But now I'm like, what is gravity again? How does this work? Okay, but I'm pretty sure this has to be a magnitude, right? So shouldn't it be the sum of the absolute values here? Or is it ab squared? It should be ab squared. I think we have ab squared. Abs 2, oh. Okay, so we have ab squared. Can I do the following? Oh, I guess I have to do ab squared dot, and then we have to add those together. Don't beat yourself down. Some of us never really got the hang of it in the first place. That's totally fair as well. Yeah, it's just, you guys know how it goes, like I would rather be the guy who's like, oh, I can't believe blah, 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 than the guy who's like, oh yeah, I totally know what I'm doing and totally not know what I'm doing, right? Like, you'd rather be the guy who comes at it and says things like, maybe not humbly, but says like, acknowledges what you don't know, and what you've forgotten and what you did know, like acknowledging where you're at logically, instead of being the guy who really never understood where they stood to begin with, right? Like, those are two completely different people. And in my mind, it's always better to be the guy who's like, look, objectively, I should know this, instead of saying, subjectively, oh, I do know this, but don't, I don't know. That's just my personal opinion, which is why I'm always like constantly apologizing and a bit skitsy. So, I mean, honestly, I'm not a role model by any means. Like, there's definitely a lot of things where I'm like, yeah, I mean, like if I was a logically acting human, I wouldn't have done that. But, it should be square root of r squared. Also, you're right. I'm working with Coulomb forces, so this stuff is back of the hand for now. Exactly, right? See, that's what I'm saying. Like, I know because Shadipto has also put a chapter in the algorithm archive. Like, I know where they're at in their education, and I know they're going to remember this stuff way better than I ever did, or than I did. Well, I do now, because I remember where I was when I was doing the PhD, and I was doing all the, research into like MD stuff with a Coulomb law and all this kind of stuff. And I was like, oh, this is easy. It took no time because I remembered it was like right there in my head. But now it's not. It's super far away, like in a galaxy far, far away, while we're doing galaxy simulations. Okay. It should be the square root of r squared. Let me just do this again. Let me take a look at 11 over here. Delete that. So how do we calculate u? How do we calculate the magnitude? So it's square root of r squared? Yeah, that's what it should be. You're right. I can just put that down. Perfect. So it should be square root of r squared, because we already have r squared. Perfect. Okay, so in principle, this might potentially have a chance, not a high chance, but might potentially have a chance at working. I reckon that chance is about 2%, but 2% is way higher than, like, I don't know, it was when all this was wrong. So let's go ahead and give this a go. I'm gonna go over here. We're gonna remove the data file that we had before. Okay, and we're gonna run it again. We're gonna go over here, right, just quit here, and try running GNU plot and see what happens. I'm hoping we get something pretty out. And if we do, then we can take a break working on algorithm archive stuff. I might actually do a brief ramble session. I don't think I have to return anything. Oh, you're right. But why u? Oh, it's u because it's... Yes, you're correct. Should be the unit vector. 1 over r squared. R is the sum. So u is going to be correct. All right, let's try that one more time. Try running that. All right, do it again. GNU plot. And now hopefully we'll at least see the particles come together. I think you're immediately going to see what I did wrong. But I'm going to show it. I'm going to show it anyway on stream, and you guys are going to immediately understand how I'm an idiot. Okay, I was wrong. I actually don't immediately understand how I'm an idiot. I thought I was going to get it, but I don't actually. All right, so they're going far away. It looks like the same visualization we just had. Maybe it didn't pre-compile, so I'll run Julia one more time. Let me bring the scale in really quick. So let's go into vi plot.gp. All right, GNU plot, and let's try it one more time. And hopefully we get something useful out. I'm not really sure. Let me get some water. Oh man, we've been at this for an hour and 30 minutes, and like, okay, so again, I was splitting the stream into 3 parts. The first part was me going to get the visualization out, and I was hoping it was going to be correct. We got the visualization out, but it is incorrect. So, you know, Mirage. I should crash as R goes to 0. Did you sum over all the particles? I think I did. Oh, hello there. So, I can't even tell, like, is the time step too large? I'm pretty sure I summed over all the particles. Let me check again. Here we have the forces. So we go to the n-body simulation. The temporary acceleration is a plus equal of the force law. The force law here is going to be gravity. So gravity here should be 1 over r squared. I think we're doing this correctly. R squared is going to be position 2 minus position 1 times position 2 minus position 1. And then we have u here. Now, there was a question a while ago about why you don't like summations, and I'll talk about that in just a second. But just remind me of that once we get this working, because that's actually a whole nother story involving GPU computing, parallelization, and all this kind of stuff. We'll get there. I promise we'll get there. But, you know, like, I want to get the forces, get that done, and then we'll talk about summation, because it's actually a long story. But look, it's shaping up. We're getting there one step at a time. Let me drop the time steps down to be like 0.01. And let's run it one more time. Okay. What my fear is that the time steps are so large that what's happening is one particle is like zooming out the other way because we're just waiting too long. GNU plot one more time, and then let's see where we go from there. And again, it's taking a while to do the visual, blah, blah, blah. Yeah, look, I could accelerate this. We're going to accelerate this, but this is kind of like just the first check, you know, making sure things work. Fabus, thank you so much for subscribing with a Prime. Let me go and put a Simulicow in chat. Really appreciate that. Obviously, I appreciate all the support everyone gives the channel. And if you can't tell already, like, you know, I have been trying to do these, you know, slightly longer streams. So this week for the past 3 days, so 2 days ago I did a 5-hour stream. Yesterday I did a 4-hour stream. Today as well, I'll do a 4-hour stream. Tomorrow I might be able to handle a 6-hour stream. We'll see. But I'm slowly trying to increase that stream time to get, what I'm hoping for is a 6-hour stream every day. And hopefully what you're also seeing is that I'm way like better at expressing myself, which is very obvious because I'm getting more used to streaming again. So I'm slowly getting back into the streaming fold. Statny Popora, what should I'm going to call you Statny. Is that okay? I'm just going to call you Statny. Thank you so much for following. Really appreciate it. Well, okay. This is still doing it doesn't look any different. I'm going to turn Julia off and on again because maybe that was a problem. I don't suspect, it might not be, but, oh, it could have been actually. Could have been because I might have forgot to use revise. Okay, let's try it one more time. One more time. We'll get it. I promise we'll get it. This is it. Last run. Like, this is a Leos Lab guarantee. This is going to work. Crap. Before I even finished the sentence, it didn't work. All right, let me try that again. Okay, we'll try it again. One more time. Once this precompiles, that will be our Leos Lab guarantee that this is going to work. Oh boy. I should never have said that. Like, just one time. Okay, Leos Lab guarantee, this is going to work. Promise. I've never been wrong before. All right, let's go here. We're going to run GNU plot. We got it. This is it. It's going to be perfect. In fact, I'm not even going to look at the visualization because I know it's going to be correct. That's how you know you're a good physicist, when you don't even care about the results. Mirage. Okay, here's our initial set of particles. And, come on. No. It looks like you're updating accelerations for each time step. Just the first one? No, I think I should be. Let me check though, because maybe not. So here we have n-body, which is going to be called when you do find accelerations. And then if we go into VI source simulate, we find the accelerations every time step. And then we also run the integrator. So we find the accelerations and run Verlet. That's all we're doing. But to check to make sure the accelerations are changing, we have output. Clearly not enough dark matter. We're not even at the stage where we're adding in dark matter. Like, we're literally at like the n-body stage. We're nowhere near where we need to go. We're super far away. It's going to take a while. Like all this stuff always takes a while. But it's good to do. Like the way I see it is, like I said, we obviously everyone has ambitions to have amazing research projects coming out. But the fact of the matter is, getting the simulation working, even if there is no research coming out, is still very useful. During the PhD, we had a discussion with a whole bunch of professors who were talking about how, hi Radu, by the way, who were talking about how, like, if you see something in a paper, you shouldn't replicate it because that's just a waste of time. What you should do is you should build on top of it. And I question that because I'm like, how do you build on top of it without replicating the results first? And so we're at that stage where we're replicating results so that we can build on top of it. And that's just how I feel like it should be done. So we're way back in the day. Like, we're literally in the 1950s territory right now with these simulations that we're running right now. But eventually, we'll get from the 1950s to the 1960s, and then to the 70s and the 80s and the 90s, and then finally we'll be in the current millennium, And then we're starting to work with stuff that actually does push the boundary. It just takes a long time to get there. And for me in particular, I'm quite far away because it's been a long time since I've done one of these. Okay, let's take a look at Source Simulate. We are finding the acceleration each time step. Let me output the accelerations as well, just to make sure they are being updated. Is the force or acceleration being applied to the particle with position 1 or the particle with position 2? Maybe that's it. Let's check. Let's go to forces here. So we're returning this. So we'll use gravity. Where are we doing? So gravity, we use n-body, temp acceleration. We do accelerations of I is equal to that. So when we run n-body, this is going to be reading accelerations and positions. And we are doing simulate.jl accelerations. Find accelerations. Let's take a look there. Find accelerations takes a set of particles. Why would it be doing pset2? Wait, we'll figure that out. Why is replication bad? He just said it isn't. Oh, actually, wait. Because I'm still struggling with this, would you guys mind like a 5-minute ramble session where I talk about two things? One, the replication thing that I just kind of mentioned, and two, the summation thing, and then we'll come back to this because, it's good to kind of derail things for a second, think about things, and come back. So I'm going to do a quick ramble session really quick. Let me do journal, new page before. Two things I want to talk about. One, we come here for rambles. Oh, good. I'm happy to hear. All right, so two things to talk about. One is summation, which I'll talk about first. So I mentioned a long time ago, like 30 minutes ago now, that I don't like sum. I don't like this thing. The reason I don't like this thing is that historically there are a few very difficult problems to do in parallel, and one of those things is a summation. In particular, something called a parallel reduction. Right. So this is one of the things that's incredibly easy to do on the CPU, but very difficult to do on the GPU. It's very difficult to do in a massively parallel sense. Even in the case where you have a single thread doing the entire summation. Okay, let's think about the two ways to do this. So we have some sort of array. Here's our array filled with numbers. And we want to compress this all into one number. We want to sum them all up and figure out what the value of all these guys put together is, right? That's what we want to do. In this case, there's two ways to do it in parallel. One is to make it so every single thread does it. Every single thread does the summation. This is fine. Specifically on the CPU, this is what you do because your threads are big and beefy and powerful and they can do a lot of stuff. But when you're on the GPU, you don't want to do that. So two, the other way to do that is find a way to distribute this. Okay, but if you were here for the histogram streams and everything else, doing this distribution across threads is actually quite difficult because when you think about it, how are you going to do it? You have to find some way to have the memory sync together. After each thread adds things together, it's kind of weird. And so the way people typically do parallel summation is they take this array and split it into two, and they do a vector addition. And then they split the sum of those two again into two, and they split that into two again and again. So they make use of the parallelism by basically having every thread add half of the array together, and then have half the threads add the other half together, and those half add those together again. There are more effective ways to do parallel sum nowadays, but this is kind of this historical way to do it. So when I say I didn't like using the sum, it was basically sum of what would essentially be a 2, 3, or 4D variable, right? So this means that we're going to have to add like maybe the X and Y positions together, or the X, Y, Z position together, or the X, Y, Z, and W positions together. So it's ultimately, 4 things that we're adding together. The reason I was afraid of using the sum, the reason I didn't like that, is because sometimes, depending on the implementation and depending on the era of Julia development, what some would do, because everyone knows that it's a poorly optimized thing on the GPU, it would sometimes do this tricky thing where it would say, oh, okay, I know what the user actually wants. And it would take the data that you're working on, transfer it to the CPU to do the summation, and transfer it back to the GPU, right? And in that case, you would have a massive slowdown in computation, because the communication between the CPU and GPU, or between GPUs, basically the movement of data through the PCI Express port, is the slowest part of your computation, right? So the reason I kind of cringed at using the sum there is because there was a time in Julia development where that's what this function would do. Now we can cancel that behavior, and I think there is a natively defined sum function, but I'm actually still not sure what will happen when we run it in parallel. I'm not sure if it's going to try to distribute that across different threads, this kind of thing, and I'm just kind of confused as to what this means. And so the reason I was worried about it was I was afraid we're going to have to rewrite it anyway by using this function. However, I think it is the current way to do it, because we want n dimensionality. We want a various different, we want various different dimensions supported, 2, 3, 4, n dimensional, essentially. Okay, so 2, let's talk about replication, which was probably the more interesting one. Okay, so to reiterate what my professor said, this wasn't my professor, it was a lecturer. We were talking about appropriate, it was a course on essentially scientific ethics, you could call it. It was more about like how to perform research in essentially 2020, right? At the time, it was 2015. And there were a lot of things that happened in this session that I kind of disagreed with. So one thing in particular, right, had to do with keeping lab notebooks, right? And you'll see how this has to come into play with other things, right? So lab notebooks are something that researchers keep in order to ensure that if anybody is trying to check their results, or if they're trying to replicate their results, or something like that, there's a very simple book that they can look at to help them recreate the exact results, right? Now, for me, my lab notebook is almost always my Git history, because my Git log holds basically everything I ever had. Which is why I also typically will leave my Git history a little bit messy, so people can see the steps where I failed along the ways, see the steps in which I failed along the way. Now, why does this matter for replication? Because when it comes to replication, even though we as scientists claim that replication is one of the key cornerstones to the scientific method, it's something that we definitely need, and people definitely want every study to be replicable. They also say that. There's a replicability crisis. They're saying that nowadays, something like 50% of studies can't be replicated. And this is a huge deal, right? Because if you can't repeat science, is it actually science? And the answer is no. But the fact is, most people will not go through a study and redo the study. Specifically in the field of biology or chemistry or physics, experimental physics, for example, people don't have the equipment. They don't have the animals. They don't have the ability to do the study again, right? And so what this professor was saying, coming from an experimental perspective, is that if you see something in the literature, you should never try to do that exact thing, because it probably took them 4 or 5 years to get that study done, or something like this, n years, where n is higher than 1. And because it took them so long, it's just going to waste your time to replicate that study. It's going to be essentially useless, because you're not going to get a publication out of it. And for the most part, if people were actually testing whether that particular study was useful or not, they probably wouldn't replicate anything. They would instead look at the lab notebooks for that particular study. So this is what the professor was trying to say, and that's fair. But this is where I kind of disagree with my particular field of study. If you can't replicate the study, shouldn't it be recorded at least? Right. So this is I'm personally in favor of every single paper having a replicability step in the peer review. I think if a paper goes through peer review, it should have been tested by more than one person. Now, in the case of software and in the case of mathematics, and computation, all this kind of stuff, that's really easy. You just redo the simulation. Now, sometimes it's hard. Like, for example, if you're using a supercomputer with 18,000 GPUs, fine, of course, it's going to be hard to replicate that study. But, small scale dynamics should be at least somewhat replicable, and you should have something like you as the author should give the readers something that they can do at least on their own equipment, whether that be a personal computer or a laser in their lab. Just give them something that they can actually test to ensure that each part of the paper actually works. Like unit testing, right? This is something that a lot of scientists struggle with, but I think that, providing unit tests or integration tests for each paper would be wonderful, right? Like saying that, hey, in order to make sure that this works, we tested all this other stuff. But anyway, this is completely beside the point. Let me pop in by finishing my thought, then I'll get to the next chat comment here. So the reason I fundamentally disagree with this replication argument, that you shouldn't replicate other people's work, is because of two reasons. One, in the replication of other people's studies, you learn how to get to that boundary of human knowledge. You learn how to go from where you're at to where you need to go to actually advance the topic further, right? And by replicating state-of-the-art code, specifically, or state-of-the-art physics maybe as well, you can just, what the state-of-the-art is now, and you can go from there. You can move on from there. And the only way you can push the boundary of human knowledge is by appropriately figuring out where that boundary is. Otherwise, you might do shoddy studies, which I see a lot of times where people will benchmark a particular result. And it's like, that wasn't really a good benchmark because of these reasons. And I know that. And they probably knew that too when they were writing the paper, but they wrote the paper anyway because they just didn't care about repeating other people's work. There's one other thing here, as far as replicating studies are concerned, though. You shouldn't replicate a study for the sole purpose of replicating the study. You shouldn't just say, I'm just going to redo this because I feel like doing it. You should have some research goal in mind. You should be like, okay, I'm doing this so that I can do something else. Like you repeat something with the sole intention of improving upon it, right? And that's fine by me as well. But there's so many things to talk about here. I don't really even know where to start. But essentially, depending on what perspective you're coming from, you could have a radically different take on what is viable to do in peer review and for replication and stuff. Why should it take the same amount of years? You already have a guide how to do it. You can just follow it, right? Of course, it doesn't apply in every field, but probably in many, right? So like I said, there's a couple reasons why you might not be able to replicate it. One is hardware. You might not have the appropriate laser setup. You might not have the appropriate animals in your lab. You might not have the appropriate high-performance computer. You might not have enough hardware. All of these reasons, you might not be able to replicate it. But outside of those logistical concerns, giving someone an experimental setup, for example, laser alignment, right? To get lasers aligned properly takes a phenomenal amount of effort. You have to, make sure all the mirrors are precise down to the nanometer. You've got to make sure that, the light is going through the lab in just the right way. You've got to make sure that it's tuned, and that, the light going through your optical fiber is as efficient as possible. There's all these little things that you have to take into account that basically mean, you set an engineer on it full time, and they can't do it in a week. It's going to take at least a month. And though it might not take years, the question is, is it worth wasting a month of your time or 2 months or 3 months to redo a study, even if it's way faster, even if it took them years and it takes you 2 or 3 months? Is it worth doing that replication? And in my mind, specifically, if it does cost a lot, I do understand their logic, where you should only repeat something if you have in mind pushing that state of the art. By the way, a few minutes ago, Sunji96 and also Asiram06, thank you guys so much for following, really appreciate it. Useless because you don't get a publication out of it. Nowadays, that's true, but I don't think that's how it should be, is it? That's also a very good question as well. And that brings up another entirely different area, which I call the publication economy. Essentially, in order for a scientist to make it in today's world, whatever you want to call it, they need to publish a lot of papers, and these papers need to be very highly cited. And so you, as a researcher, are paid in two ways. One, you're paid by money, and two, you're paid by publications, because publications allow you to continue your academic career. If you don't publish, you probably cannot continue your academic career, specifically if you're in that angsty postdoc stage where you're trying to find a professorial position or something. Or you're starting to open your own lab. Getting more relevant papers allows for you to get better grants and stuff like this. So it all kind of works together, and you really do need to get those papers out. And so, as much as I hate to say it, modern research is about pumping out papers, and I love papers. I really do. I genuinely love papers. So it's not like I'm against this, but it means that sometimes you get people publishing for the sake of publishing instead of publishing because they have something interesting to say. So I don't know. It's such a hard topic to really tackle. But the fact of the matter is, right now in academia, if you're not getting papers out, you're losing the battle. It's going to be hard for you to get a job. Just got the tail end of that topic, but one interesting thing people are talking about for math papers is including machine-checked proofs for theorems. Yeah, I saw that before, and I think it's actually quite cool. I'm totally in the... I feel like, yes, you should definitely check theorems that way if you could. Okay, we're almost done with the ramble session. Positive results over published compared to negative result ones, it's a bias. Yeah. So that's the other thing, right? So you have journals like PLOS One, and to some extent like open source journals like the Journal of Open Source Software and stuff like this, which no longer care about the number of citations. They don't care about citation count. What they care about is the utility of the research, in which case negative results, null results, are equally as important as positive results. Now, are they going to be as cited? Probably not, but they are useful, and this is something that people are definitely acknowledging. And the same is true for software, right? Software is the foundation of pretty much every area of academic research now. Sure, there are some areas that are still pen and paper. There are some areas that are still purely experimental. But for the most part, you need software to do your research, right? And a lot of times this software is ignored because the people writing the papers are usually also not software engineers. They don't understand what the software is doing at a core level. They only understand the higher level. And so recently I'm kind of including myself, but I know I'm not actually the person that's doing it, are kind of trying to push for software being citable, being useful to the overall academic community and stuff like that. And things like this, trying to get academia to be more than just publishing novel results, but also publishing the software necessary to do the research, publishing null results when they come, understanding that, taking a year or two to write code is equally as valid as taking a year or two to write a paper, understanding that academia is more than just paper writing, is something that has been going on. It's an ongoing discussion that will continue to be ongoing for the next few years. Anyway, that's a ramble session. I talked about summations. I talked about the replication. Let's go back to the galaxy simulation. Okay, so the reason I took a ramble session was because I was lost and I don't really know what to do. So I wanted to take a second just to think. What is the problem here? So if we look at the most recent results, here we take a look at, I think I'll just run GNU plot. Yeah, let me run GNU plot one more time, and then I'll take a look at the most recent results. We'll see that essentially up here, these particles should be affected by gravity. So that means they should be coming in, and then they should be exploding out. There were a couple questions as to why they're not doing this, and that's kind of what we're trying to figure out. So let me take a look at Mirage. And so hopefully, if this is working, they should come together, but they don't. So see, they immediately spread out. 1 second. Give it a second. It's, here, let's go up here. I think it should be on. Okay, give it a second to load. I'm with you. I'm working as a student on a complicated optimization that is turning into 3 papers, but I'm pretty sure the code will never see the light of peer review and the public. If you could, I would recommend looking at the Journal of Open Source Software. It's a nice place to put open source software specifically to solve this problem. So I would recommend it. I've published there before. If you're using the software for multiple publications, it will probably be cited, highly cited. I don't know what you want to call it, but it'll be cited enough. And as a student, it's good to get started, I don't know. That's just how it is. Again, people are slowly but surely recognizing the utility in things outside of just direct paper publications. Here we are. So here's step 1, here's step 2, 3, 4, 5, 6. So they just immediately spread out. And so let's just keep working on this. I sadly have no say in the matter. I'm just a code monkey. That's super unfortunate as well. That's kind of how I felt during my PhD. Statney, by the way, thank you so much for the subscription. Let me go ahead and put a SimulCow in chat for that. SimulCow. Thank you so much for the support. I really appreciate it. For the record, people who might be just jumping in, they don't know what this project is. Again, I'm Dr. James Schloss. What we're doing is we're trying to really do an open research lab. We're trying to create an open environment to do research in by engaging with the community and just showing what research is like. And sometimes it's like this. Sometimes, you spend all day trying to figure out force laws that you knew when you were a kid but don't know anymore. That might be what it is. But hopefully by the end of the day, we have some sort of valid N-body simulator working. That's what I'm hoping for. And if we get that, I'm happy. So probably what's going to happen, we've been at this for about 2 hours now. I will keep working on this. Hopefully we'll get it working in the next 30 minutes or so. Then I'm going to take a break, work on the Arcane Algorithm Archive, where I'll focus on the Metropolis algorithm, which was recently put in by Shadipto, who's currently in chat. I'll just read through it and just kind of work on it a bit, chapter review, stuff like that. Then I'm actually not sure how much time we'll have left, so we'll see. But we should have enough time to at least think about how we're going to parallelize this and kind of sketch out what we need to do from there. Let me get some water. Okay, so there was a comment by Shadipto before the ramble session where they mentioned that maybe we're not updating, maybe we're putting the acceleration in the wrong spot, which is totally fair. Let's go into VI source. And let's go into simulate. So what's going on here? Every time step, we are basically finding the accelerations and then we're integrating things. So finding the accelerations here. Okay, so what I want to do now is go back into the accelerations.dat and just check to make sure these are actually updating with time. And it looks like they are. I mean, here's the initial acceleration. Here's the acceleration at time step 2, time step 3. Let me just go down to the bottom here. And you see that we have very strongly negative. Oh, what is going on here? What is all this? Oh, it's because we have 1,000 particles now. Oh, wait a minute. Let me check this again. Let me go and remove .accelerations .dat. Let's go over here and let me also remove check.dat. Okay, and let's run it one more time. And then let's take a look at the accelerations file. The 3-body problem was solved for 2D planes, right? But can it do 4D plus? I have no idea. If I'm completely and totally honest, I don't really know anything about analytical results. I should, but I don't. So we have -4371, -864 something. All right, let's just go down a bit. Okay, -8107, -5380. So look, the accelerations are changing with every time step. Let me go up. And you can see here, actually, the accelerations are quite high. I think I figured it out. Maybe. How about checking if the energy is constant throughout the simulation? Yeah, we could do that, but I don't want to have to do an energy check. One second. Let me go back into simulate. Actually, forces here. Source and then forces.jl. We have the sim type here. So we have the temporary acceleration here, and then we do accelerations of I is equal to the temp acceleration. We just saw, when we were looking at it, the accelerations were like 1e to the 7th or something like that at the very end. Yeah, so I think you guys are right that maybe we're losing energy, but I'm just trying to think here. So what's probably happening is that we are... Okay, so the particles are just leaving and they're constantly adding to that acceleration as they go further and further out. This could be an issue down here, so let's take a look here. So we have the acceleration 2 is going to be dot equal to acceleration 1. Try to flip the sign of the acceleration. Yeah, I could do that. Sure. Oh, what did I just do? Okay, let's just do that. X. Write that, go over here. We're going to remove check.dat. We're going to remove accelerations.dat. And let's try running geli.run. Over here, GNU plot. What are the defined masses? Right now, all the masses are defined as 1. We're not doing anything like it's all just 1. We're literally just doing 1 over r squared. That's all we're doing. There's a lot of stuff left to do here. This is just like a very simple initial test. We just started this yesterday, and we only spent like 2 hours on it yesterday. So we're like literally just starting. Let me go into Mirage. So I flip the signs of the acceleration. Okay, good. And let me see what happens. It still does the same thing. So that's the problem. I don't actually understand. So let me go into the accelerations. Let me also drop the number of particles here. Remove accelerations. Let me run Galilei.run with only 10 particles or something like that. Sure, 10 particles is fine. And then let's do like 100 time steps. 10 time steps is actually fine. This is fine. We can immediately see what's going wrong. So let's go here. Let's take a look at accelerations.dat. So we have an acceleration of 41820. We have an acceleration of 13222. So I mean, it looks like it's just constantly accelerating in the same direction. Yeah, it's just getting higher and higher, which is not what we're looking for. Let's go here. 1 second. Let's go ahead and remove star.png. That should be fine. Obviously, there's an error with the code. We only have code, right? Sum of 1 over 1/2 mv squared over all particles. See if it's constant. It's definitely not constant. We know it's not constant. So for the sun's gravity, it would be tiny masses, but crazy number. Might need more particles. Well, so right now we have 10 particles, right? And then they're just constantly accelerating in some direction, right? So we're super far. Like I don't think any physical argument is going to solve this problem. Like we're well before we start adding any physics in here. Is what I think I'm trying to say. So I'm going to VI and simulate source simulate.jl. So we find accelerations of the P set. The accelerations are changing. We just checked. Wait a minute. No, we did not, because I'm an idiot. Well, no, gravity must be applied. Otherwise, you wouldn't see things moving about. We check.dat, accelerations.dat. We run it one more time. Let's quit here. And let's take a look at the accelerations.dat. They're all 0, which is fine. Then we have 6.56 times 10 to the negative 7th. And then we have negative 1.55 times 10. So the accelerations are still changing. However, they're super low, which has me wondering why the particles are moving so far. Using the acceleration vectors before summation. Right, I did just check that. I'm pretty sure I am. So we go here to source and then forces.jl. So here I create a temp acceleration equals 0. I add them together and then I set the accelerations equal 1. So I don't I think this is not something that I think we can like dig up another n-body sim. Feel free if you want to. I also have another n-body simulator that does work that I can look at. It's just I kind of want to do not do that, you know. Okay, so let me think here. So there could be something wrong with the relay integration here. We have the positions of 1 times 2 minus position 2 plus the acceleration times dt. So our dt here is 0.01. So at most what we're doing is we're changing the positions by... At most what we're doing here is we're changing the positions by something times 10 to the negative 7th, right? Let me think. If the acceleration is something times 10 to the negative 7, how are we... Is it times 10 to the negative 7 or times 10 to the 7? It's times 10 to the negative 7. So how are we moving so far? Like, we're on the scale of 10 to the 8th, right? Let me check that again. Accelerations.dat. No. Let me do... let me go into VI GNU plot. I think I only have 10 time steps now, so let's go ahead and just plot 10. And now let's do GNU plot. And then we're going to do Mirage. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have position 1, we have position 2. So that means we have the position before. Maybe I'm just not keeping the position before correctly. That could be also the case. So set of forces here. Oh, let me take a look at simulate.jl. All right, so we have pset 1, pset 2. So what could be happening is that pset 2 should just be a copy of pset 1. Okay. P set 1's not defined. That's because I'm an idiot. P set with an underscore. What? Undefined P set 1 not defined. Oh, it's just P set. Method or no method mentioning copy for particles. Cool. Okay. I'll create that really quick then. But I think this might actually be the problem. So let me just go ahead and double check. So we want to do initialize particle number. So we should just be able to say particles of P set dot positions, P set dot velocities, P set dot accelerations. Misspelled accelerations. Let's go ahead and run it one more time. Perfect. Let me go ahead. Did I remove the files? Just double checking. Run it again. Let's go here. Quit. Now we're going to take a look at GNU plot, Mirage. Okay, this is what I was expecting to see. Them barely moving at all. And let me just double check the positions here. Okay. Change the grid extents. Remove this, remove that, change the grid extents. Now we're going to try GNU plot, Mirage. Oh, well, now we're too small. GNU plot. All right, let's change the grid extents here. Yank to yank, paste. Comment these guys out. One second. Okay, so now let's try running GNU plot. Then we're going to run Mirage. Okay, they're still too far apart, which is fine. Let's do... Actually, let me check the accelerations really quick. What do we have here? So I think we're actually getting some physical results now. Physical results. I think we're getting correct results now. Might be that they're all the same position. Right. So what had happened before, I think, was that I had initialized the pset 1 as different than the pset 2, which means that I think the difference between position 1 and position 2 was just super great, right? Which meant that they had like a really big movement in some direction to begin with, which then meant they had a really big movement in that same direction. And so I think, yeah, so I think that was the problem. I think the P sets were too far different. Let me take a look at the accelerations.dat. These are now very strong accelerations, and we're seeing no movement at all, no change at all in the acceleration, which is not... Okay. Well, I was wrong. Whatever. Why is there a position 1 times 2? So you have position equal to 2 raised to the number of iterations. Wait, what do you mean? Why there's a position 1 times 2? So you have position... equal to 2 times the number of iterations. So what we're doing here is just a simple Verlet integration scheme. I don't know, maybe I'm answering the wrong question, but it is good to mention for people who may not know. So it's literally just this. So the x at t plus delta t is going to be 2 times the original x minus x of the previous time step plus the acceleration, and then plus some O for error term. O delta t. So this is that. I'll go ahead and paste it here. We're just doing Verlet because it's like super simple, and you just like, we're literally doing the simplest of everything right now. We're not even like trying right now, and we're still failing, which is really unfortunate. So in this case, position 1 is going to be equal to position 2. So if position 1 is equal to position 2, then it should still change based on some acceleration. So it should still be moving, but it's not moving. And this could be... let me just try removing some stuff really quick. Remove check.dat. Accelerations.dat. So there should be one now. There is not. Perfect. Okay. Galley.run. Grid extents 1. Let's increase the time step as well. Okay, so now what we're going to do is we're going to take a look at the accelerations here. We have a very, very high acceleration for some of them, which makes sense because we're 1 over r squared, and if they're under 1, that means like you're going to be like 1. So if the distance is like 1 over 0.1, you're going to get like 10. And if you square that, you get 100. So you should expect to see incredibly high values here, which is what you see. Take a look at the positions for check.dat. And we see these positions are not changing at all, which is not what you wanted to see. Why are we not getting changing positions now? Is it because we should have, so the acceleration here is going to be, okay, let me just check really quick. We did have the positions changing just recently, but now they're not changing anymore. Is that because I didn't do a copy? Let me go into this guy. Let me modify this so it's a copy of this. And the other two are also copies. I don't think this could do it, but maybe it's like a, I don't know. If this is the case, I mean, I really do need to create an initialization function for, all right, I'm just kind of covering my bases here. So we're going to go here, remove check accelerations, remove check.dat, run it one more time. Let's see what happens now. If I go into check.dat, the positions are now changing. Perfect. Okay, so we have changing positions. Wonderful. We have some pretty crappy positions, but they're changing. Okay, we're getting there. All right, one step at a time. Let's go to remove the check.dat again, remove the accelerations.dat, and we're going to run it one more time with a much larger grid of 10. And now we're going to do check.dat. 47745, okay. Okay, let's go to vi plot.gp. And let's give her a go. 1 second, we're almost there. GNU plot. Mirage. I don't know what I was expecting, but I'm not sure what it was, what I'm even looking at. Oh no. Okay, wait. Is our time step too big that we don't see the small scale interactions? What? Okay, let's increase the grid extents one more time as well to 100. Let's go ahead and, I really should have it so when we run things, we just we erase the existing files. I should do that, but I don't do that right now. So we're gonna try it one more time. GNU plot Mirage. Okay, let's take a look at check.dat. Great. Okay. What happened? GNU plot? Mirage? Oh, there's nothing in the box now because I made the box 10 times bigger. There we go. So we have these guys moving around. Okay, that's not particularly great. Looks like gravity is missing. What do you mean gravity is missing exactly? Like we're definitely... Now, is that the appropriate direction for these guys to move in? So we're seeing some movement. Let me plot this for a few more time steps. So we're gonna run 100 time steps, I believe, here. I've got to remove the... I should put those in at least the same line. So now let's go into VI plot. Plot for 99. Run GNU plot. Now we're gonna run Mirage. And then let me just see what happens. So we scroll in. So why are those guys, what's going on with these two particles up here? So yeah, what's going on here? Did you flip the acceleration sign back to minus? Might not have. Yeah, I might not have. All right, that might be the problem. Okay, let's go back to source, forces, and I did not. Thank you. Okay, let's go back over here. I'm gonna remove this, and then we're gonna remove check.dat. Oh, I can't. Okay, right. That was stupid. I need like an ampersand, right? Okay, so now what we're gonna do is run that, run over here, run GNU plot, then we're gonna run Mirage. Okay, so we have all these particles. Okay. I'm really not sure what's happening. All right, let me make this a bit bigger. Here we go. Oh, that did nothing. All right. Okay, well, whatever we're doing, it's wrong, which is good to know. Okay, so we have these particles in here. What is going on there? Why are those two, like, spreading out? Okay. Yeah, they all just want to run away. What? Weird. Let's see, what do we have here? How the heck are you simulating 4D? Anything without a massive assumption of what 4D means? I mean, you don't really have to assume anything for 4D. I mean, it's not hard. It's just 4 spatial dimensions, right? Yeah, whoosh. So like you're literally you have X, Y, Z, and then you just assume another plane, which is, W, right? And so you have X, Y, Z, W, and then you just do the simulation as if you have 4 spatial dimensions, and then you project it back down to 3D. Now, look, I mean, sure, we can like make all these assumptions and stuff like that, but yeah, the easiest way is just to don't think about it too much. Just assume you have a 4th axis, like Ethan says, and just go with it. Just do the math, and then go back to 3D, project it back onto 3D to see it. I've got a video out on YouTube for understanding 4D that kind of shows the math behind it, how you do a projection and stuff like that. It's a quick 3-minute video. I guess I can give it to you now. YouTube.com. And let's go to my channel. Should be up here. Your channel. Then let me go to videos. Most popular. And it'll be this one. Here. Yank yank. Paste here. Optimization goes into very large dimensions. Math all works under the same gradient descent. Same for gradient. Yeah, right. So that's the other thing. Like, there's a lot of definitions. A lot of people say 4D is time, which is kind of true if you look at like Minkowski space and stuff like that. Fine. But we're not doing that here. We're assuming 4 spatial dimensions, and you could imagine it 5D if you consider time as well. But I'm not doing that. I mean, it's literally just 4D plus time. That's what we're doing. Right now, we're working on 2D plus time. We're just getting started. It's going to be like a month of work to get there. Maybe more, actually, because apparently I'm really, really bad at this. The problem is, like, every time you read papers, you're like, oh, it's so easy. Anyone can do this. And you could do it because you've done stuff like this before. But the problem is, like, I've lost all of my physics capabilities. I suck at physics right now. So I'm, like, really far behind where I need to be. So, yeah, what is going on here? Let me start with just 2 particles. So we're going to remove these guys. I don't understand. How do I do 2? Oh, can I just remove this? Will that work? I think that would work. Yeah, okay, that's what I need to do next time. Just remove 2 files. I don't know why I was trying to run 2 commands. So what we're going to do next is we're going to run with 2 particles. So instead of 10, it's just 2. All right, we go over here, we're going to run GNU plot, and then we're going to run Mirage. So here we have our 2 particles in space. All right, let me make it a little bit bigger. Okay. And now we just see what they do. They are doing nothing. They are literally not moving. Great. Wait, no, wait a minute. There was a movement, a very small movement. Let me try making the box a bit smaller. Something like this, maybe. Oh, I think I see what's happening. Yeah, let's run this. So we're going to run that. Let me remove this. Now we're going to run it again. Now let's run GNU plot. Now we're going to run Mirage. Oh, they're too small. Okay, let's go into plot.gp. I think I see what happened. I think I see exactly what's happening here. So what's happening is the the particles that we were seeing beforehand were so far away that they weren't feeling each other's forces at all. And the ones that were close enough together were actually kind of coming together, but then they got so close that the force ended up getting really, really big, and then it just zoom out, I think is what we were seeing. Let's go here, right and quit, and let's go into GNU plot, and then we're gonna run Mirage. Okay, so we should see, yeah, so I think, let's drop the time step to be like 1, 2, 3. I have to remove everything. Now we have to do it again. And now let's do GNU plot and then Mirage. Sorry. And then we should hopefully see, come on, do something for me. That's not what I was expecting. Let's do this then. GNU plot, Mirage. Okay, so here they're quite close together, and hopefully we see them come right up close. I don't know why they're moving upwards, but they should come, no. Okay, wait, maybe that was what we were expecting. Wait a minute, that could be it. Wait. Okay, so we see, I'm not entirely sure why they're moving upwards, but we do kind of see them coming together, and then I think like at some time step like this one, they just zoom past each other, and they actually flip, and then this. So what I might want to do is I might want to plot each point a different color. Right, so it's that straightforward. It's just another axis, but how do forces like that work? In gravity act differently when accounting for the fourth dimension, like something pass through an object. Yeah, so nothing can pass through another object in 4D. That doesn't happen unless you project it down to 3D, in which case you might see a pass through, but in general, the collisions will act the same. We will probably change the force of gravity, so it's 1 over r cubed instead of 1 over r squared. I think that just comes out of doing an integral across 4 dimensions. And stuff like that. So the thing about orbits, I'm not sure if orbits are stable with the new force law. So this is why we might actually keep the old force law but run that in 4D. It just depends on a bunch of things. So we're not there yet. Like we're working towards the 4D stuff. Jinktastic, by the way, thanks so much for following. Really appreciate it. Collision would occur when the positions are the same, right? It would just work more than 3 axes. You check the value. Luckily, 4D is much bigger. Less chance that they come close to each other. Well, yeah. I mean, this is also kind of fair. Okay. 2 particles with 0 initial speed should just move towards each other. Right, that's exactly my question as well. I don't know why they're drifting at all. So we're clearly doing something wrong. I mean, I'm trying to imagine it as someone who lives in 3D world because things are going to appear and disappear from my point of view. I mean, it depends on your projection, right? Like this is what I keep saying. It really depends on how you project that data back down to 4D, which is why I sent the video, because I talk about projection matrices there. Like that's really the only thing. It depends on how you convert 4D to 3D. This is a good point of discussion. Let's go ahead and talk about it. So how do we convert 4D to 3D, right? Right. So in general, the way this works is you have some 4-dimensional vector, which is going to be X, Y, Z, and W, right? So some 4th dimensional axis. And this is going to be a 4x1 vector, right? And so if you want to project this onto 3D, the way you do this is you multiply it by another vector in here, which is some 3x4 vector, right? And if you do this multiplication, it comes out with a 3x1 vector, which will be your X, Y, and Z component, right? So depending on how you do that projection, you can have things pass through each other. Like for example, if your projection is just taking X, Y, Z and ignoring W completely, then you'll see stuff pass through each other. But if you do the projection matrix like stereographically, then you should technically see all the data. It's just distorted. So here, I'll just show you that. I should be able to find it here. Let me do this in should find it. Stereographic projection. Okay, so this is that projection here. I think I show it better in the video. Yeah, I definitely show it better in the video. I hate all this. Okay, let me go to the video really quick. Shh. Shh. Quit showing me ads. Okay, this guy. So you literally just multiply by 3x4 matrix. And so like, for example, if your 3x4 matrix looks something like this, you'll end up getting a projection back into 3D that does have things pass through each other. See, this is what you see there. Here, I'll just show it here. But if you change that projection matrix, you'll get different results. So if, for example, you change your projection matrix to look something like this, then you'll get a result that, one second, yes, here. So it's resembling a shadow cast against the screen, so you can technically see most of the data. But yes, so depending on what your L is, you should technically be able to see most of the information, right? Now, again, it is compressing all that data into 3D. So, like it's still different, like it'll look different, but like the data will be there. It's just kind of one of the dimensions will be squashed into the other dimensions. So that's what's happening there. Right. I mean, I'm trying to imagine as someone living, right. This is complicated because I remember 4D imagining of kids' toys, the ones where you put a cylinder in a circle shaped hole and the star shape in the star shaped hole. And that projection has stuff moving in and out, floating and disappearing. Right. That's what I'm seeing, a shadow 4D object. Ignoring an axis is like looking at a shadow cast by some parallel light in that direction. Right. So I do understand this is complicated, specifically because you have things like, for example, that very popular video with the 4D toys showing that things pass through each other and stuff like that. And you have all of these complicated people who are like, oh, 4D is just adding an axis, which is also equally as complicating. But like, really and truly, like if you think about the projection, you look at 4D, you're just like, you just imagine there's a fourth axis, and you think, okay, how am I going to get that data in 3D? Oh, I have to multiply by a matrix. Oh, okay, I get it now. In order to multiply that by the matrix, we have to compress down. Like that's the most intuitive way to think about it. I think all of these things that are trying to like glorify the fourth dimension, and they're trying to like, show people that like, oh, look, there's these 4D toys that pass through each other and all this kind of stuff. Like it sounds cool, but it really does make it difficult to understand, which is, again, why I made this video. It's like a quick 4-minute video, and I understand. It was like 5 years ago that I made the video, 6 years ago almost. No, 5 years. So I'm not saying it's like the best video. Like, honestly, there's definitely stuff about it that's quite, like, I would probably do it differently if I did it now, but it's one of my first videos I ever made. But, like, there is a, it's not something that, like, the more you try to put intuitive arguments on, the harder it's going to be to understand. Like literally just look at the math. The math is you have a four-dimensional vector, a 4x1 vector, x, y, z, and w. You want to get that into 3D? How do you do that? Matrix multiplication. And then once you look at that, it's like, okay, it's intuitive. Now, to be fair, everyone has different intuition, right? So for some people, maybe this argument of things passing through each other in 4D, maybe that's totally fine. And maybe that works for some people. It just didn't work for me. Now, if you look at the comment section on this video, like, look, people are pissed off. Like, people are like, this doesn't make any sense. Some people are like, this is the most jargon-filled video I've ever seen. Or like, it's impossible to understand. And I get that. I do get that. Like, everyone has a different intuition here. But, I mean, I genuinely think this is still the easiest way to understand what a 4D object is. Just looking at it as a 4D thing, and then seeing that and projecting it down. Like, I still stand by the video. I would have deleted it by now if I didn't stand by it. Anyway, I know I keep encouraging you to watch my content, and I know that's not what I want to do. I've given you that exact content in stream form, so you don't have to go watch the video. But that's what it is. I like how you get unreasonably annoyed at that video by that video's comment section. It's just because, like, a lot of the other videos, when people see them, they're like, oh, this gave me a new intuition. But that video, no matter what, every single comment that people have on that video is negative. And I'm like, screw you guys. I don't get it. Like, literally, there's no better way to explain 4D. You can argue with me all day. You can argue with me. But I don't think there was a better way to describe 4D than what I put forward in that video. And I still stand by it. You can make as many arguments as you want, and that's fine. But for me in particular, that's what I needed to understand it. And that's why. So let's see. What do we have here? The best way for me has been 3D slices of 4D volumes, like in an MRI. Yeah, so my main issue with that is that you need all of the slices to see the 4-dimensional video. And so you have to see like a time series of 4D. And so I mentioned that at the start of the video, that this is kind of an intuitive way to see it. But in essence, you're still looking at a 3-dimensional object, not inherently 4D, right? And I get that the projection is still projecting it down, right? And the thing is, a slice is still a projection, right? That's the projection matrix I showed at the start with like the 1, 1, 1 instead of the LW minus W line. So I don't know. Anyway, so much effort. It would be better if they didn't give a crap or said they didn't get it at all. Well, a lot of them say they didn't get it. The thing that gets me is that like when a video goes viral, so that video has 4 million views. So when a video goes viral, right? You don't get, you get the bulk of YouTube watching the video. And if the bulk of YouTube watches a video, they're not going to be there and be like, they're not going to say positive things. Like, that's just not what happens, So yeah, baby rage, that's what people do. It's fine. Like, it's totally fine. Like, I get it. It's just that, like, that particular video, like every other video, I get somewhat positive comments on, but that one is the one that people are like, they're just mad at, It's your fault. I don't understand. Right. That's it. Like, the other thing too is it is a 4-minute video on 4D. Like, to be fair, did you expect to understand everything about 4D in a 4-minute video? Probably not. But if you have a high school level education, that is to say you've been through linear algebra, which I did in high school, so I thought most people did as well, then you should have been able to understand it to some reasonable level of certainty. Again, maybe college linear algebra is what you need, but to some extent, it's like, you should know how to matrix multiply, I guess I was almost lucky. I was almost lucky that I had to learn all the math when it was never about position or geometry, that when starting to think about 4D spaces, it made more sense from understanding the math already. Right. I mean, this is, I don't want to do too much more rambling here, but there was a article that came out like yesterday or today or something that I read saying that they're like no longer going to be teaching algebra in like middle school for people in California. I'm like, why? Like, you're taking the most useful part of education out of education? Like, everybody uses math. No matter where you are, what field you're doing, you're gonna use math. Whether it's intuitively, just by looking at the geometry of a space, or is rigorously, as in you're doing it in engineering, you need math. It's fundamental to everything that you do. And it's the only field that when you learn more, you genuinely are able to do more things with that immediately. Like, it is immediately applicable. And I know I'm ranting here. Science, history, literature, maybe literature you could argue is immediately applicable if you argue that you need to learn a new language, but pretty much everything else, it's like, it might be clickbait. Actually, you're right. It probably was clickbait, but it's just like, man, like you're taking the only useful part of education out of education, man. I don't know. That or to troll, to be sarcastic as well. I guess I almost lucky. Yeah. So I read that comment. We only did a little bit of vector stuff in high school here in Germany, nothing involving matrices. See, that's super interesting. I was in the middle of like Alabama, like rural Alabama. I can't even say the word rural. That's how rural I was in Alabama. And so like, I assumed that if me in the middle of Alabama learned about linear, like how to do matrix multiplication, I just assumed everyone else learned how to do it as well, because like, and I realize that's a poor assumption, but like, it's like, where are we in education that like people don't learn this? Anyway, I'm being super biased and privileged with the knowledge that I have and stuff like that. No, many districts are taking out accelerated classes because the students in it aren't fitting a quota. There's also that as well. It seems pretty logical to me. 2D square root of xy, 3D, 4D is add w. Yeah. In my high school in Germany, we did quite a bit of matrix multiplication. Remember the CRT and other BS going on, Common Core? What is CRT actually? I don't know what CRT is. You can't be that privileged in rural Alabama. I mean, look, I was pretty privileged. I was, top of my class. I was valedictorian of my high school. Like there were 500 other students there. And, there was a group of people that wanted to learn. There was a big enough sample size that there were people that, there was a big enough sample size that there were a group of people that were dedicated to learning, and it was nice. Let's see, what do we have here? Rural Alabama, I'll have to show you another time. Critical race theory. What's critical race theory? Chinese remainder theorem. Chinese remainder theorem. What is that one? I don't know what these are. Cathode ray tube. Click-through ratio. Maybe. I only know CTR as click-through rate. Even then, that isn't privilege. You were top of your class. That's also merit. You worked it. Is it work though? I don't know. Look, I mean, here's the truth, right? Like, I genuinely believe that look, I'm not talking about race. I'm not talking about ethnicity. I'm not talking about any of that. I'm talking about the fact that I was a person that was raised in a middle-class household that had enough money so I could go do swimming every morning. I could live leisurely. A lot of my friends weren't that way. A lot of my friends lived in trailer parks. A lot of my friends did not have enough money to support themselves, and they had to work through school just to get by. I didn't have to do that. I worked because I wanted to, not because I had to. And there's a dramatic difference between me being able to spend time studying, having the luxury of finding academic papers easily on the internet because I could afford internet, having the ability to waste time reading papers, like all this stuff that I did in high school, like learn Linux, all this kind of stuff is because I was fundamentally privileged in my ability to do this. Like there aren't, like I had a fundamentally good childhood. Like could it have been better? Yeah, but like I don't know. I feel like that's a fair argument to make. And so when I say I'm privileged, I acknowledge that. And I also acknowledge that, I came from the US. I didn't come from another country that, has a fundamentally different policy on education. Like, sure, maybe Common Core isn't great, but it meant that people actually got through classes that they needed to. For example, the new math that they're teaching is actually fundamentally useful. Like a lot of the stuff that they're teaching for new math that a lot of people hate was kind of how I thought of math anyway. You kind of need to teach multiple different methods in order to train something up. So I think we're actually making good strides in math education, even though some people might be taking out algebra or whatever from middle school. I do kind of trust that they're replacing it with something that's actually more intuitively useful. It's just that I was being ranty, and me, I end up ranting about things. Maybe, but has there ever been a person that had a rougher go, but has achieved a similar? But has there ever been a person that had a rougher go, but has achieved a similar, if not greater strides in academia? Oh, definitely. What I'm saying isn't that, the argument of privilege, and I shouldn't go into this. I'm sorry. I don't know why I'm talking about this. But the argument of privilege is not that, because I had such a great, the argument of privilege is not that I, being someone who grew up in an upper middle class household, is definitely going to succeed, or I'm definitely going to fail. And it's not saying that someone who grew up in a lower class household will definitely fail or definitely succeed. The argument is that the die were stacked towards me, right? Obviously if I had more money, it would be more stacked towards me, but maybe not. I don't know. The fact is, I had a good chance because of that, whereas other people don't have a good chance. So is something from the 50s? You may mean something else. Oh, okay. I'm sorry. I might mean something else. You're totally right. I might mean something else. What I mean is that recently I've been seeing on Twitter a lot of parents getting angry about certain calculations that people were doing mathematically, because I follow math education Twitter. And so a lot of parents are getting upset. A lot of teachers are getting upset that they have to teach parents the math that they're also teaching their kids. And a lot of the parents are getting upset because they don't understand the math that they're teaching to the kids. So there's just a lot of back and forth with the math education recently. So when I say new math, I might have meant something else. I mean that maybe it is Common Core, but recently the way in which math has been taught to children has changed in the past 10 years. So the argument of privilege is loaded because it seems reduced to that in common parlance, and even decisions on making policy. And that may explain why such accelerated programs are being dropped. Then again, I may be a cynic and have other biases. Yeah, I mean, that's the thing. As long as you're acknowledging your biases, I do the same thing. It's kind of that's the argument of privilege. It's look, the fact that we're sitting here and it's look, I'm biased for these reasons. It's just acknowledging that, hey, when I make these arguments about academia, I make these arguments about, doing 4D simulations. I make these arguments oh, this is super easy. I make that argument knowing that I'm biased. I'm biased because, I spent all my time learning as a kid. I'm biased because of all these other reasons, right? And that's the argument here. Acknowledging where we are and why we're there. That's my whole argument here. And that's what I use the word for. I don't really know what else privilege is loaded for, but that's where we're at. Your parents definitely seem to have had enough capital and cultural capital to greatly increase your chances to succeed. Yeah, that's all I'm saying. That's it. All I'm saying. True, but biases and being factually correct aren't mutually exclusive. Bias and being factually correct aren't mutually exclusive. Yeah, that's... Yeah, of course. Yeah, you can be biased and factually correct. That's fine. Yeah, of course. But they're two completely different arguments, right? Saying that Newtonian's law of gravity works is yeah, sure, that's a true statement. Newton's law of gravity works to some extent. It obviously doesn't work. When we talk about quantum regimes, or we talk about like super like galactic scales. Sometimes it doesn't work at that scale either. Like, fine. Sometimes you have to treat light as a wave, sometimes as a particle, fine. Like there are things like this, right? And some people have a bias towards treating one or the other, but the fact is that bias leads them to certain regimes where discoveries can be made. And I don't know, like I guess my point is, like you can be an incredibly biased person and still produce really good results in science. Newton, for example, was an incredibly biased person, but he produced really good results. I mean, that's just how it goes, Anyway, I'm rambling a bit. Give me 2 minutes. I'm gonna be right back. You may be correct for the wrong reason, which may even be worse than being completely wrong. Okay, that's happened to me a lot though. Like, I don't know how many times I just kind of guessed at an answer and ended up being right. And then people are like, why is that the answer? I'm like, oh, this is the reason. And it's a completely wrong reason. Like, there's absolutely no reason it should have worked, but it did. And when that happens, exactly like what you're saying, you end up building upon like a web of lies that like, you finally, when you try like extrapolating further, it's like, oh, wait a minute. I mean, the best story of this, my favorite story with that is ether, AETHER. Right. So it's such a wonderful story in science education that I wish they would teach like teenagers, because I love it so much. The idea is that way back in the day, I think it was Socrates, said that there were like a bunch of different elements. I don't remember, like water, fire, earth, air, and a final one called ether. Ether was kind of this binding force of the universe. Well, it was like this goop that we all live in, something like this, like soul or spirit or something. Basically, it was kind of a waste of time, and you couldn't really test it in any way. It was just kind of this thing that existed. But in the 1900s or something like this, it came back into the world of physics. People were like, wait a minute, maybe this ether thing actually does exist, because they couldn't fundamentally understand how light as a particle worked, or how it could possibly like act in the world, right? And so like, there were all these theories about how light propagates in the ether and how like it acts as a particle in a wave because it's waving through this ether goop that exists in the world and all this kind of stuff. And ended up being that this theory of ether completely wrong, because there were so many people that were so biased towards this result. They so wanted this result to be exact. There were so many papers published about this one thing, and people were so sure it existed. And they did experiment after experiment, and every single experiment failed. Every single experiment showed that the ether didn't exist. But people were so biased, they so wanted ether to exist, that they kept fighting for it and kept fighting for it until the Michelson-Morley experiment, I think in the 1930s, maybe the 1950s, I don't remember. But this experiment conclusively proved that ether didn't exist. It's known as the greatest null result in history because of this. And it's one of those things where, like, when you think about the biases that exist in academia, it's just a wonderful story to express how even if you want something to be true, or if you build something up on premises that maybe aren't exactly true, eventually you'll figure it out. And it might take a lot of effort, but you'll get there. Let me change my video device really quick. Here and there. I think there was a video audio desync. Okay, I'm going to take a 2-minute break. 1905 was when Einstein published. Oh, maybe it was 1830s. When was the Michelson-Morley experiment? Look, I mean, you guys are Michelson-Morley. When was this experiment? Michelson-Morley experiment was 1920s. Yeah, 1920s. 1887. Oh, 1887. You're right. 1887. What's the 1920s? So they continued to experiment. So they repeated it. The 1920s was the last one. I see. Got it. Perfect. That makes perfect sense. You guys are totally right. Somehow I must have thought 1920s because, I don't know. You're right. I should not have thought 1920s. I got the year wrong. Which is kind of why I am skeptical to reducing everything to social and economic capital, because there's many exceptions, and even then some of that is hard to measure. Right. It was like a very reasonable assumption at the time, but out of the dang self-awareness or skepticism. Wait, I don't actually know what you're getting at there. I'm sorry, I might be missing something. At least people that used the Standard Model knew that it was based on an assumption, until it was proved the Higgs boson actually existed. Right. Right. I mean, I think these guys knew they were working on assumptions too, right? You always keep your premises close, right? You're always like, okay, whenever you're talking to someone, you always know this is the premise that we're fundamentally working on. And when you talk to a new person, they're living in a fundamentally different reality with a fundamentally different set of premises. So when you're talking to them, it's usually not so much like, when you talk to people, it's not so much about like, arguing that your set of premises are correct. It's more about figuring out where they're at, figuring out what premises they're working off of, and then working with them. And so, like, sometimes we had a discussion just the other day on the difference between like parallelism and different threading terminologies and stuff like this. And the fact is, people have fundamentally different ideas that are very conflicting about what this stuff means. So, economic and cultural capital do increase chances. Chances of problem. That's the problem with sociological things. They usually work on the population level, and it's hard to study that influence on the individual scale. Yeah, that's fair, right? I guess assuming that everyone believed in ether didn't acknowledge their premises, right? I think they did. To some extent, I think they knew that there was a hunch, there was a premise here that people didn't. Anyway, it's always good to just take a second, think about like why you're arguing for this thing, and then be like, hey, actually, I don't know if I necessarily believe in this premise here, or maybe that one's a bit faulty, and that's kind of where you start pushing boundaries, Anyway, I'm gonna take a quick break, just 2 minutes. We're gonna come back. We're gonna get this working today. Like, look, we've been working on it all day. Oh, well, not all day. I've only been streaming for 2 hours and 40 minutes, but since I started streaming today, we've been working on this, and we're gonna get it working. I really want to get this working today. So I will be right back. I'm just going to make this big. I'll be right back. Give me a second. Okay, I'm back. Let me go ahead and catch up on chat. People in their field. Oh, I missed some stuff. All right, I guess assuming that everyone believed in ether, and some very good predictors are called problematic, or there's a lot of crazy in that field, and there's no shortage of money seekers. Yeah, I guess I see where you're coming from. People in their field usually know when a subject is BS, but when you got to publish, those usually make for easy papers. Maybe that might also be true. Or clickbait, or political funding, or other. Even when people have been exposed as frauds, some of them are kicked out, seem to stay like a bad rash. Yeah, look, I mean, this is true. Like, not everyone's like, yeah, I don't know what to say. I mean, you guys are right on the money sometimes when it comes to like what you guys are saying. Okay, so just to catch everybody up, I have about an hour and 20 minutes left in stream. I'm going to cut it off right at 8, which will be about 4 hours of streaming for today. I'll come back tomorrow after that's done. But what I want to do today is get this simulation working. So what you're seeing right here is a simple two-dimensional N-body simulation. I'm not calling it a galaxy simulation. It's not a galaxy simulation yet. This is literally just the start, the seed of a galaxy simulation. So what we're doing here is we are taking a bunch of particles, and they're all being influenced by each other's gravitational pull. So if I pause this for a second, this particle here is feeling the force of every other particle here and is accelerating, and should be accelerating, towards the bulk of particles. But that's not happening. Right now, as you can see, everything's just spreading out in the distance, which means we have a lot of work to do. So what I'm going to try to do in the next, I don't know, hour or so is just figure out what's going wrong with this code. And why it's breaking and all that kind of stuff. So just before going on our little ramble session that we did the simulation again, but just with 2 particles. So here's the 2 particle simulations, and we see right now we've started the particles out with 0 acceleration. They shouldn't be moving anywhere. And it should be that they only feel each other's gravitational pull. That is to say, they're only moving closer to each other and no one else. But as you can see, for some reason, they're accelerating upwards, and I don't fully understand why. Up and to the right, up and to the left, sorry. And then somehow they're being repulsed also at this stage as well. And I don't understand why that's happening either. So these are the 2 things that we need to figure out. We're going to keep going with this 2 particle test case and just see what we can do. So we're going to work on this for the next hour. It's clearly like twiddling signs and stuff like that. Pilipale73, hey, how are you? I hope you're having a wonderful day. You came in just the right time as we reintroduce the project that we're working on. It almost looks like there is some external force that makes everything accelerate away from the origin. Right, but where would that be coming from? Where would that be coming from? Literally, the acceleration is like, I don't know. Oh man, let me just take a look at the forces. So let's think about what's happening here. At every point in time, each particle is looking at every other particle, right? So let's take a look at that function. We're going to go to the VI source forces.jl. So to find the acceleration, we run our simulation type, and in this case, our simulation type is n-body. The reason we've done this is because, in principle, we could have other simulation types, like, for example, the Barnes-Hut method, or we could use a k-means clustering method, or something like this. There could be stuff in the near future that mean we do a different type of simulation. So we run n-body. We say for I is equal to 1 to the length of positions. So that means we have, this is going to 1 to the number of particles. Maybe space itself is expanding. We're definitely dealing with that. That's what we're doing. Change their initial positions. Aren't they drawn to each other? The initial... Right, so I randomly initialize them. They're at different initial positions. You could try with a fixed acceleration to debug the process. Yeah, we could. Let's just do that. So let's just do acceleration is equal to negative 9.81 meters per second squared. Return... and we're just going to do negative 9.81, negative 9.81. Actually, in principle, we should just have them fall downward, shouldn't we? So maybe let's just have them fall in the y direction here. So they're just going to fall downward. That's what we're looking for. And here we're going to comment this out, and this out. It might have to be a vector in the end. Yeah, so it might need to be this. Okay, that still didn't work. No method matching plus for int64, vector of float 64. What's going on? The gravity has position 1 and position 2, where position 1 and position 2 should be xy coordinates. It should just be a vector. It should be a vector of... Wait. Maybe we're grabbing this wrong. Maybe... how big are these guys? So let me go into VI source initialize. So here the particles are going to be particle number along the column, and then the dimensions this way. So we're grabbing a 2x1 vector is what it looks like we're grabbing. Let me just double check. And to do this, we're going to grab forces here, and I'm just going to output the size of position. So we're going to do print line. Let's just do position 1. Position 1. Let's just do position 1. Right, let's go over here. We're going to run it one more time. And it's outputting that. So let's do size of position 1. We have position 1. And so this should give us 2 accelerations. One in the x direction, one in the y direction. So how is that different? Let me do size of position 1. of position 1. And this gives us, size of position 1. Size of position. Wait. I see what's happening. It's a single int64 value. Oh, how interesting. Okay, that explains some of it. So what's happening is when we broadcast this out, it's being broadcast incorrectly. That's useful. Let's figure this out. We're going to get there. I think we're going to get there. I think it's because we're doing the following. So it should be this, I believe. Galley.run. Give it a second to recompile. So it's 2 comma. So that's actually moving the right direction. Let me see. I missed something. Let me go ahead and catch up in chat. You could try with a fixed acceleration. No, I'm not. No, I'm wrong because they're still not. They'd still not go up to the left if they repel, right? So the limitation of the int has to be some weird rounding stuff. Yeah. So I think what happened was. So let's see. No method mentioned plus for int64 and then vector of int64. Okay. Good. I think we're getting there. Let me try going back here and seeing if I can do the following. So let me go there and comment this all in. Go this, run it one more time. Okay, so now we have some issues, which is kind of okay. This should be a dot times here. Dot times, try it again. No method mentioning plus. Where's the plus? We need a dot plus, that's fine, but where is the plus? This is going to be in forces line 22. Here. Oh, dot plus equals. So temp acceleration for temp acceleration is going to be equal to 0. No, that's the problem. It should be zeros of, it should be reading in a dims, shouldn't it? But we have the accelerations. So it should be size of positions, and then it should be 2, I believe. And that should do it. And now down here, we're going to do dot plus equals. All right, let's try that again. Okay, 2 by 2 matrix at 3, 1 to 2. Okay, we're slowly getting there. We are slowly getting there one step at a time. So for the record, what had happened was I was being tricky with Julia and trying to read in, essentially our vector for the particles is going to be number of particles in this direction and the number of dimensions in this direction. So it's a 2-dimensional vector. And so what I was trying to do was grab just the top element of that 2-dimensional vector and read that in. But what I accidentally grabbed was just one element instead of the top row. And so the problem here is that I'm trying to read in the full row and I'm running into issues with that. So we're slowly but surely getting there. And I think that's fine. So attempt to access 2 by 2 matrix float 64 at index 3. Why are we trying to access that at index 3? Is that because I'm grabbing the wrong values? Let me try running this again for 3 particles. Okay, attempt to access 3 by 2 matrix at index 4. How are we going to 4 indices? Temp acceleration, 4i is the length of positions. I see, it should be size of positions 1. Also, why is that there? So let's do size of positions 1. Try it again. Okay. Cannot convert an object of vector float 64 to an object of type float 64. Okay, I think we're slowly getting there. It's just a matter of working through these little bugs one step at a time. Oh boy, I'm gonna be so happy when we get this done. I'm really excited for this. So now we have array.jl forces line 24. Oh, right, so this should be accelerations, temp acceleration is equal to that. So accelerations of I think it's gonna be colon, is gonna be temp acceleration of colon, and this should be a dot equals. Try that again. Okay, well, it's running, it's just breaking. Have you thought about using software and game development category instead? Yeah, so for the record, there's a fundamental reason I don't use a software and game development channel, and instead I use science and tech. And the reason for that is that I'm really trying to grow a community of researchers on Twitch. whether they do computer science, they do physics, they do biology, I really want more people to do research. And I feel like software and game development is not necessarily the best place for that. Plus, way back in the day, we used to have a separate programming channel and a separate game development channel, categories, separate software and software programming category and a game development category. And frankly, I feel like it just makes more sense for me to be away from game developers. It's not that game developers are bad. I follow and I watch a lot of game developers, and we raid game developers all the time. It's just that it just doesn't feel the right category for me, because I'm fundamentally doing research, right? I'm not fundamentally making games or writing software. And so for that reason, it's like, do I really fit in with software and game development if I'm not writing software and I'm not doing games, but I'm primarily doing research? I don't know. I think science and tech fits a little bit better. And I do fully understand that I'm doing a lot of coding. I'm doing a lot of programming. But for me, that programming is a tool. It's like, for example, if I were to draw a comic, but I do that completely programmatically, I feel like that should be in the art category. Even though technically I'm doing programming, I don't feel like the thing that I'm making is like, I'm not making science and tech. I'm not making software and game development, even in that case, But again, I'm totally willing and accepting to I accept people's argument that they come to this channel expecting science and tech and they get programming. I guess that's fine as well. Have you thought about using software and game development? Yes, he has, and still prefers to stay in science and tech. Purely Pally 73, thank you so much for following. Really appreciate it. It's cool. Thought I'd mention it. A lot of people are not aware of it. It doesn't seem fully accurate. It's also not just game devs. I wish there was some software development category myself. Science and tech is very appropriate. However, we're not making game. Right. That's how I currently feel. I'm willing to change on that. I sometimes I feel like maybe I should just be in just chatting because I do so much rambling. And of course you're right, because I do a lot of programming. Maybe I should be in science and be in software and game development instead. But I asked people on Twitter, I had a long discussion about this, and we ended up deciding science and tech is where I should stay. So the steps of software development, are the steps of software development the same as the stages of grief? I think they're slightly different. What are the stages of grief? It's like anger, denial, stages of grief. Stages of grief. I don't actually remember what they are. There's 5 stages of grief. Whatever, I accept, sure. It's denial, anger, bargaining, depression, and acceptance. Yeah, I don't think programming gives me any of those feelings. However, debugging, that's something else entirely. There should be a Laos category that should solve the problem, right? Maybe bargaining. No, honestly, programming and software development is usually a joy. Like, honestly, software development, reading papers, for example, this is all stuff I genuinely like doing. And so I never really get any feeling of grief for that. But debugging, maybe. I'll sometimes get, yeah, okay, it depends. I don't know if I feel any of these things during debugging anyway. Either. I think what I do get the stages of grief from are like deadlines. So for example, if a deadline's coming up, this is probably what I do for deadlines. First, I'm like denying the deadline exists. That's the procrastination stage. Then I get angry that the deadline exists. I'm like, oh, now I have to do this thing. Then bargaining is like, oh, well, maybe I don't have to do the full thing. Maybe I only have to do half of it. Then depression when I'm actually doing it because I have a deadline coming up. And then acceptance that I'm not going to meet the deadline. That's my 5 stages of grief. That works perfectly. Before like programming and debugging, if I'm just doing it for fun, I don't know. I don't usually get that so much. I actually usually enjoy my time. Even like doing the PhD, I enjoyed it most of the time. What's the next one? This is going to be Forces line 22. Really? You don't like this one? What's wrong with you? Attempt to access a 3x2 matrix at index 4. Why are we going to index 4? We have 4j is equal to 1 to the size of positions 1. Should this be size of positions 2? Why are we going to index 4? Yeah, why? I don't understand. let me output the size of positions. So we're going to go up here. This print line isn't working the way I wanted to anyway, so let's just go ahead and comment that out. And let's go in here and let me just print line size of positions. Oh, I'm an idiot. I got it. I'm so stupid. Earlier, I was like, why are these lines indented? I don't understand that. I just indented them. And now I'm like, clearly there was like an I and a J in this loop. Oh my gosh, why am I so dumb? All right, what do we have here? This might be just C, but I find myself bargaining with C. That's fair. C compilers are that way sometimes. That's fair. I'm so stupid. It should be length. This is size of positions. Now let me think. So what are we actually doing here? So we're going through I. So we're going through each particle. So this should also be size of positions 1. Okay. So we're going through all the particles. Setting the accelerations. So where's I? I is there, J is there, so this should in principle run. It ran. So let's go ahead and remove some stuff. Try running it again. Moment of truth. Moment of truth. We have the 2 particles. Oh no, is it working? Okay, they're moving away. They're not moving towards each other, but they're moving. G loop is the wrong size? Could be. 1 second. They're moving away from each other instead of towards each other. But should be indexed with 2 instead of 1. Should it be? Let me see. I think they should be. I think it should both be 1 because we're going through each particle and then we're looking at every other particle. And so it's an n squared, I think. So I think that's still correct. Let me try changing this to be that. Remove galilei.run. Does this make them come close to each other? Mirage. Okay. Are they coming close to each other? Yes. Okay. We did it. I say knowing that we didn't do it. Okay. Why is this backwards? It's because U is a position 2 minus position 1. Why are all the accelerations negative? Okay, all the accelerations are not the right, like all the accelerations are the wrong sign. I don't exactly understand why. This is why. So this needs to be negative here. And then this guy, we need to change J and I. Why does temp acceleration use index 2? Right, so what I'm doing, so what's happening is we have accelerations, positions, and all of these as a 2-dimensional array. So along one dimension is going to be your like x, y, z coordinate, and then along the other dimension is the size, right? So your temporary acceleration is going to be an acceleration in x, y, and z. So it should be along this array. Julia's column major, so size 2 is going to be this way, and size 1 is going to be this way. So 1 is along the number of particles, 2 is along the dimensions. So you want temp acceleration to have an x, y, and z component, or w component, just an x, y component. And then you want to basically add to that every step. And I think all I need to do is switch this, so it's J, which is the current particle we're looking at. No, yeah, I just need to switch these around. So it's this. Yep, that's what we need. So let's try running it again, remove this, galilei.run. This time I'm gonna run it for this. Okay. Quit, right, quit, GNU plot, P Mirage. Okay, there they go. Bam, yeah. Okay, perfect. Okay, this is exactly what we want to see. So what we see here is 2 particles slowly come together. And then, bam, they hit each other. So this is not how collisions work in real life, just for the record. Definitely not how collisions work. But because we're doing a really dumb force law, what's happening is as they're super close together, the 1 over r squared value becomes really, really high. So they end up shooting it in opposite directions. So now what I want to do is run this very same simulation with a lot of particles. And we're just going to mess around a bit and try to get a nice visualization. And then hopefully we have something that's kind of sort of working. And that's all I care about in life. Something that's kind of sort of working is about like gold star for me. Like, you know, some people are like shooting for glory, you know, like they want their name in gold, you know, they want a Nobel Prize. I'm just looking for something that kind of sort of almost works half the time. Like that's my gold star. That's where I'm shooting for, you know? See you later, alligators. Have a wonderful rest of the afternoon or evening or morning or whatever time it happens to be your time. I'm gonna get some water. We're gonna keep working on this, get a nice visualization to put there in the upper left-hand corner. Yeah, then we got an n-body simulator working. Sure, it took 6 hours when it normally only takes, you know, 2, but we got it working. So that's all that matters. ACICL, thank you so much for following. Really appreciate it. Okay. You can set f equals 0 or if R2 is below some threshold. Right, so what we should probably do is some form of, it's not called dampening, softening is I think what we need to do. I don't think it's too hard to do. But yeah, we could just set f equals 0. If this ends up being a problem, we can do that. But I think in the end, we actually want to do some sort of softening. Let me actually write that down in the notes. Oh. Okay, work on initialization to ensure the particle acceleration is actually correct. I think we're done with that one. So DG, and what I'm going to do here is say, in particular, add softening and constants. I'm just going to put this down in the next line. Add softening, add G constants. Okay, write and quit. Good. Okay. Whew. Need to take a quick second to just, you know, like, it's one of those things. You know, you spent all day working on something stupid, right? Like, the n-body simulator is something I've written so many times before. Like, genuinely speaking, it was one of my first research experiences as a kid. So yeah, like the issue here is that, you know, doing it again 10 years after I did it for the first time, should not have been a problem. I should have been able to write it in 30 minutes and it took 6 hours, which is really unfortunate, but it also shows that, you know, everyone gets tripped up. There's always going to be problems that come along and, you know, you're just gonna have to fix it, you know? So time to simulate 100 particles to do the video. Yep, that's what we're working on next. I just have to make sure we get the right time scales and all this kind of stuff. For softening, yeah, I think that's it. We just add an E parameter and E can be whatever we want it to be. The reason I'm not doing it right now is because I'm not sure if this is a parameter we want to read in or if we just want to add it in there. I don't know. So I'm going to think about it because there's also another thing I want to think about, which is how to add these optional arguments that certain force integrators might need, whereas other force integrators don't. And so, for example, if I want to switch from Verlet into Euler or Runge-Kutta or something, how would I do that? And what would that additional argument look like? And I think I want to workshop that when I think about adding softening to the forces. So that's why I'm holding it off right now, because I think it's easy. I think we just add like 1 over E plus R2, right? I think it's easy. But I want to think about how that workflow will go. And so I wanted to put kernel abstractions in first before doing that, because there might be some issues with kernel abstractions and doing like all these tricky function arguments and all this kind of stuff. So that's kind of my thought right now. I'm probably going to change it tomorrow. But right now, that's kind of what I'm thinking. Okay, so for this, what do we want to do? Grid extents 10. We're going to do 100 particles. Let's see what happens. Okay, go over here. Let's go to VI plots. Change the grid extents here to 10. Okay, and 99, 100 time steps. Perfect. So now we're going to do GNU plot and see what happens. Mirage. So here's the initial distribution of points, and I don't know if that's correct. Oh no. Okay. I think maybe it is correct actually. So let's see. So I think what's happening is that there's some particles that move really fast. So here the particles that are close to each other are coming together. So like, let's watch this pair right here. So that pair right there is coming together. And then we're going to see right now it splits apart. Oh, that was a bad pair to choose. Let's look at another pair. So let's look at this pair right here in the corner. So it's going to take a few time steps. 1, 2, 3, 4, 5. And then right here, they start to split apart. And this guy spreads out. Okay, so we are seeing the correct physics here. We're seeing the correct behavior. I'm not going to call it physics. But we need to make the grid extent smaller. So let's just do that. So let's change this to 1 again. Now they're probably too close, but let's just see what happens. So now we're going to do this, run it one more time, and then we're going to do plot.gp, change this to be this. So this means they're influenced by every other particle in the simulation, and then we do GNU plot, and then we do Mirage. Okay, so these guys are crazy. Right. So let's try it again. Great sense of 2. One second. This is, I mean, look, this isn't the ideal way to do it. I'm just trying to get a nice video. There. Here, quit, GNU plot, and then we're gonna run Mirage. Okay. So here, they're just doing the same thing as before, which is what we expect. We expect all the particles to come in and then come back out. Maybe just look at 4 points on the corner of the square. Symmetric systems like that should move towards the center. Right, that's true. I could just initialize them all as like a circle, and then we should see them all come in. Yeah, maybe we do that. Let's just put them all as a circle or something to begin with. Right. So how do I do that? I think I could create a new initialization function. I mean, what happens if I just increase the number of points? Oh, that was stupid. I'm running an n-body simulator. I'm like, what happens if I increase the number of points? Obviously, it scales like by n squared. That was stupid. What was I thinking was going to happen? Oh, this code that's taking a second to run is now going to take, obviously, 2 or 3 minutes to run. All right, let me try it again. But this time with 1,000 points. I think this one's actually runnable. Oh, but then we have file I/O to think about as well. It should still be doable, right? Let's go ahead and remove these guys. Try it again. Let's just see how long it takes. You and me, together. This will be fun. Square is easier. Put them in... Right, yeah, I could do that as well. It's technically a circle with 4 points. Yeah. We'll do that in a second. Like, if this takes too long and ends up being stupid results, we'll do it. Yeah, we should definitely do it. But I do think the underlying methods are working now, which is good. It's just a matter of kind of messing around with them and playing with them a bit, and seeing where we go. So, again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. No, I do apologize, Shadipto. I was planning to do the chapter on the Metropolis stuff today as well, but I just don't know if I have enough time to go through that as well. So I might call that and do it tomorrow. Maybe, yeah, I might call it and do it tomorrow. Yeah, let's just see what happens. Mirage here. So here's our 1,000 points, and we should see, yeah, that's kind of what I expected. Right. Yeah, perfect. Wonderful. Okay, let me increase the grid extents a little bit. This is just really stupid. Let's do GNU plot and then Mirage. That's all good. We know this is what coding is like. Yeah. So it spreads out like that, which is exactly what we expect. I guess we should wait for it. I think what we should do is we should run a simulation that goes for long enough that we see it relax back in. That's what we should do. Yeah, that's what we should do. I think. Will it relax back in? I mean, if the particles go so far away... No. We should consider this the other way around. Let's change the grid extents to be 5. And then what we're going to do is run with 100 particles. Run that. There we go. Do it one more time. Hey, Gibbous, how are you? If you're messing with the grid extents this much, maybe make that a parameter somehow. The grid extents are a parameter. I change it every step. How come it's square and not a circle point? It just initializes them as a random distribution, or like a random uniform distribution in a square. That's just how I did the initialization. I could do a, what's it called, Box-Mueller transform to put it into a circle. Are those particles forgotten if they go out of bounds, or they're still calculated? So that's why I just wanted to increase the grid extents a little bit for the... Oh, you're talking about the grid extents for the GNU plot. Yeah. I could do that, but nah, it's fine. Okay, so the grid extents now are 5. And I want to... Oh, I already removed it, so I should just be able to run GNU plot here. And I should be able to just do Mirage. So here's all the points, and we see them kind of spread out, which is, I guess, expected. Maybe I just run it for a bunch more time steps is maybe what I do. Well, actually, let's just see how far these particles go. So let's go to viplot.gp, and let's just go out to 100 or something. GNU plot, Mirage. So here they all are to begin. Oh, they go super far out. And it looks like they're going to continue to accelerate for a while, which is fine. Crew watch yesterday was nice. Sound crew has a lot to fix though, apparently. Oh, I'm glad it went well. Yeah. I'm super glad it went well. Another thing you can do is to increase and decrease the mass, faster and slower dynamics. Right. Yes, increasing the mass. Wait. Increasing the mass here. What does that do? Increasing the mass. We want... Yeah, wait, let's just do it. Let's just do it with slower dynamics, because I think that's actually what we want. I think you're right. So let's do vi / source forces, and here's what I'm going to do. I'm going to multiply you by 10. And you guys are going to have to deal with that. So we're going to do Galileo.run, go over here, quit. Now let's do GNU plot and take a look at Mirage. Did that do anything? Does that actually do anything? Like if your mass increases by a factor of 10, but all the masses increase by a factor of 10, then your force increases by a factor of 10. So you move 10 times faster. You want to divide by a factor of 10. Right? Decreasing mass for slower dynamics. Right. I'm an idiot. I'm a complete idiot. I was just stupid. I was like, yeah, you're right. Oh, this is me forgetting. 0.001 didn't work because there's a comma. All right, try it again. GNU plot. Mirage. Wow, beautiful dynamics. I've never seen such amazing dynamics before in my life. Oh, it's just incredible. Here are all 100 frames put into a wonderful video. All right, let me change the grid extents. Vi source forces. All right, let's go into vi plot.gp. Modify this so it's 10 by 10. GNU plot, Mirage. All right, so we got here. Here we have that. I mean, is this correct? I guess. What's wrong with frame 0, by the way? I mean, okay. Sure. I'd buy that. I mean, I guess it's fine. All right, let me try it again. I'm going to change the grid extents here to be 2. And then we're going to go here, vi GNU plot, plot.gp. And then we're going to go here, modify this so it's 2 by 2 again. I mean, look, it's just a matter of messing with the forces here. GNU plot, PDF, Mirage. Okay, so we should have these guys. I guess it's fine, honestly. They shoot off at great speeds because we don't have a dampening on it. Let's add the dampening to it, or the softening, and just say screw it. And we're just gonna add softening now and not worry about it. So it should just be, we can just do r squared. 1 over r squared. What do we need to do here? So it's 1 over r squared, so we just add 1 to this. I think that should do it. Looks like you really need that dampening. Acceleration is just exploding. Right, yep, that's fine. We'll go ahead and add that in. I think this will do it if we just add a +1 to the 1 over r squared. We do some here, so I think we can just do that. And no, we want to do 1 over r squared here, so we want to add it this place. A bad hack would, yeah, we could do that, but I think, let's see, you really need dampening, r squared, 1 second. Multiply the whole thing by r squared over 1 over r squared. Do we, okay. Return, sure. Thanks, by the way. So we're gonna multiply this by, but isn't that, we already have the r squared in the denominator. So isn't that just gonna cancel out the r squared? So can't I just put the r squared here? And won't that do the same thing? Yeah, you're right. We're adding dampening. You're right. Right here. Go there. Galley.run. Okay, right. That didn't work. You're correct, PEMDOS. Well, they're coming together now. It's all coming together now. Wonderful. It's a dumb softening force. I get it. I keep calling it dampening as well. I mean, you guys are right. Let me do that again. That. Run Galilee.run. Go over here. Quit. Now we're gonna do GNU plot and Mirage one more time. This is gonna make the move way faster, but with the softening, it should be fine. All right. That ain't bad. That's a thing. Looks almost good. Almost. I mean, not quite, almost. Okay, I'm happy enough with that. Good. Done. Done with life. Nothing else left to do. We're going to run that for 1,000 time steps. Lego. Lego. And then we're going to make that video, put it in the upper left-hand corner, and call it a day. Oh, my gosh. Jeez. Okay, so we're going to do, what do we have here? vi plot.gp. I think the X range is fine. It changes to be 999. Right, quit, run GNU plot. Then we should have all the images, so then I have to run Mogrify to negate everything. It should be good to go. Needs to run much longer to get some balanced state. Right, we're just going to, it doesn't need to be balanced right now. We're just kind of looking for something that kind of looks pretty is kind of what I'm looking for right now. I know that's kind of lame, but I like to have something playing in the upper left-hand corner. So when people come in, I can be like, this is what we're working on right now. Okay, so the next thing I should be able to do is just run the last Mogrify command, which should negate all the images so we get them in the color scheme that I want for the background of the of my stream. And then I just turn them all into a video. Okay. Let's go. It takes a second. Sorry, I was really excited, but now we have to wait for a minute. So, it's done. Okay, good. I was almost left with my own existential thoughts. That would have been awful. So what we're gonna do next is run the last create video.sh. That's what I want. We're gonna run that. I'm going to remove this video in there. Then we're gonna run this. Do yes. Go over here. Run MPV. Let's see what it looks like. Okay, we still need to let it run for longer. What do you guys reckon? Should we just do a long run? Give it 5 minutes to do its thing? Oh, I see what happened. I'm a complete idiot. I'm gonna do this one more time. So we're gonna remove the old acceleration file. Then we're gonna run it again. And then we're gonna do it one more time. Because I think that video was actually quite good. We just have to do it again. So GNU plot. Give it a second. And we could let it run for a while, but I think this will be good enough. You'll see in just a second. It only started to get interesting. Right, so we're gonna run this. We might do it for longer. Just give me a second to Mogrify it, and we'll let it play. And then it should be nice. Again, I've been streaming for about 3 hours and 30 minutes, 3 hours and 20 minutes now. So I think probably once we get this video done, I'll commit everything. We'll kind of talk about what's left to do in the project, because there's a lot left to do, and I want to kind of figure out what the appropriate direction for everything is. Create video.sh, yes. All right. Yes. Oh, I see. I had to create 2 palettes. Yeah, I gotcha. So let's go here, MPV, full screen that boy. All right, let's watch it. 3, 2, 1, and go. Okay. I mean, it looks nice. I think it's going somewhere. It's a long enough video that we can put it in the upper left-hand corner, and people are gonna like that. It's gonna look nice, I think. Yeah, there we go. That's it. We have the normal dynamics. Yeah, happy with that. I think it looks nice. Okay, so that means our N-Body simulator is probably working okay. Wonderful. How long does this video go? Okay, there we go. Let me move it up here. My video might lag a little bit, but I can fix that. Wait, there, I don't think there's a video audio delay, but I think that's okay. It's very satisfying to watch. I'm pretty happy with that. Okay, whew, we got there. Okay. So let me go ahead and commit what we have. And yeah, I'm happy enough with this for the N-Body simulator. So we've got a lot left to do, like a lot left to do. And there's questions about where we go from here. So that's why I think it's important to just kind of open up Zernal PP, just kind of jot down our thoughts, think about where we want to go, and what people are actually interested in doing here. So let me cd backup directory. Let me do git status dot forces readme aux. So what's going to be an aux? So git status aux. There's nothing in aux. There should be something in aux. What if I do git add vi.gitignore? There shouldn't be .dat. So let's also put a star.png and a star.mp4 in here as well. And then I think everything else should be fine. So git add dot git status. Okay, so we have the aux create video.sh, which I think I do want to commit. Plot.gp, forces.jl, simulate.jl, readme, and the git ignore have all been changed. Hit commit. -m, fixing small bugs with Verlet N-Body. All right, that'll work. There we go. All right, git push origin development. Whew, okay, this is the first test. We could use 3D grid and see if it eventually becomes planar. I think we are gonna have to let it run for a long time for that to happen, because I think the only way, no drifting either, so energy should be conserved. Right, so I think the only way to get that 2D disk is if we, screw it, let's just do the 3D simulation. Let's see what happens in 3D. Let's go. Actually, let me remove these guys, and then we're gonna go. Oh, I just deleted, I went off Julia. Okay, let's see what happens in 3D. I don't think you guys are gonna like it, but we'll do it. We'll do it anyway because Shadipto says we should, and obviously, yeah, revise. Using Galilee, perfect. All right, let's do it in 3D, see what happens. The 2D disk happens with collisions. Is that not necessary? The collisions aren't necessary. What's necessary is the angular momentum eventually rotating a bit. You need that rotation is what you need. I'm actually not sure what to do to go from a random distribution of points to give it that rotation. I think it might take a super long time before that rotation starts to form. So anyway, let's go ahead and give this a go. Yes, so we have this, so we're gonna run Galilee in dims equals 3, see what happens. And then over here, we're gonna cd into aux, ls here, and I think what I can do is just go into vi plot.gp, add a z range here, and then just change this to be splot. And I think that'll work. I don't know, let's see. Would giving the particles an initial vector help? Yeah, so if you give it an initial spin, then yeah, we could almost certainly, I think we could create that 2D disk. But also in order to create the appropriate like spinniness to it, we definitely need like a bit of dark matter in there. So let's see what happens if I take a look at the Mirage here. So here's our 2D particles, or 3D particles. They're coming in together. I mean, look, I think this visualization is cooler than the other visualization. We need to figure out how to make the box square. I'm not sure how to do that. Yeah, let me just put this simulation up there, because this is... yeah, you start with the rotating disk. I'm pretty sure you need that. But we don't have that just yet. So we can give them an initial velocity vector, but... okay, actually, I'm going to make this the video we have in the upper corner, because that looks cool. Let me do setting square cube GNU plot. I just don't like the... It was like squashed in the Z direction, right? So I didn't know how to make it not squashed in the Z direction. It's a cube. So set style is set PMD, depth order, hidden 3D, set PMD3, and PM3D implicit. I don't think that's what I need. I thought this was pretty simple. Let's go to... Oh, maybe size? Going from 2D to 3D was extremely painless as well. That's nice. Yeah. That's how collisionless galaxies... I could technically go ahead and do the 4D simulation if I want, but it's going to look exactly the same as a 3D. Set size square, set ratio 2. Scale length, set size ratio 1. Set size square, set ratio 1 is probably what I mean. Cheat by having a black hole manually rotating around the center. Yeah, so we could do that already. We might do that tomorrow, actually, I'm not sure. Set the same ratio in all directions independently of the window. Set size ratio -1 is what I guess I want. Let's go ahead and try that. Yeah, plot. Open, paste, comment this out, right, quit, run GNU plot one more time, and see if this does it. It was just the grid was like weirdly spaced in the Z direction, so I want to do this one more time because it was giving the appearance that we were creating a spiral galaxy when we weren't actually. Let me get some water. Ooh. Starting it with some non-zero velocities would do it. Let me do Mirage out.png. It's still... What is going on? How do I make it not... How do I make it scale appropriately in the Z direction? I set the Z... Set GNU plot. VI plot. Set Z range to 2. You could start them off with some non-zero velocities, but then you'd have to make sure the center of mass velocity is 0. Yeah, so... Set view equal XYZ. Let's see if that does it. All right, give it a second, and we'll take a look. And then hopefully we'll just have a cool visual, put it in the upper left-hand corner, and that'll be that. Good, we're slowly getting there. Slowly but surely getting there. So let's do Mirage. Okay, well, it's now a bit too square, isn't it? Yeah, why is our... Okay, I'm gonna ask a stupid question here. This is what I do. Why are we so far off the... You know what I mean? Like, here's 2, -2. Why is it not right there? I mean, look, the visual is better, but like, we're so far off the axis. Why are we so far off the axis? Set size equal. So the points don't overwrite the base. Oh, okay, that's probably fair. Yeah, okay, that's fair. Yeah, let me take a look at the visual as well. Is that actually what's happening? You are right. It's not doing that. I mean, maybe it's fine. We can keep it this way. It's okay. I don't mind it too much. How do I fix that though? Z-axis offset. GNU plot. Maybe this guy. Oh no, it's a PDF. Oh no. That's not what I was even looking for. No, this is the problem. Anytime I have to do any plots, it's like all of a sudden the entire stream just becomes plotting. Position of z-axis label. I could offset the graph, I guess. Let's just go here. Position z-axis. Remove the empty space and splot. That's what I want. Set XYZ plane is it help? Set XYZ plane in 1. XY plane 1. VI plot. Open. Paste. DD. Okay, try it again. Right quit. We're gonna do GNU plot. See what it looks like. Hopefully, looks pretty good. We might need to change like the image size or something so that it, like I just want to scale a bit better. That was the only thing. It's just, I mean, I guess it's fine. It's fine. Let's just see what happens. Mirage. No, it got worse. Oh, geez. I wanted to get closer, and now it just runs away from me. What is going on? I mean, does it even matter? I just thought. Maybe -1, yeah. I genuinely thought I had it. I was like, oh, there we go. That's it. We got it. We're going. And then it just changed the right thing in the wrong direction. Right. Maybe this music would be cool for your video. He allows to use all of the music in YouTube for Twitch for free. Yeah, so I already have music that I prefer to use in my videos. Let's do... Are you talking about Wintergarten, by the way? I'm not looking at the video, but maybe. Someone else suggested that as well. Mirage. Okay. We're getting there. Almost. It's upside down, but almost. All right. We know what to do now. It needs to be 0. All right, try it again. Run GNU plot. This has to be it, right? Has to be it. Let me see what the YouTube channel is, by the way. So the music that I use, I actually quite like. It's by Josh Woodward. Oh, I don't know who this is. But yeah, the music that I use right now is on Josh Woodward. joshwoodward.com. I just like the music. I think it's nice. Everything's Creative Commons. So that's the music that I like. I've been using it for a long time. So it's under all my videos. I could maybe change, to a different artist eventually. But for now, I'm still quite happy with it. Okay, here's a visualization. Wintergarten with a marble machine. Right. Okay, so now the only other thing I want to say here is that I think the visualization is nice, but I wish it took up more of the screen. So I could, yeah, I wish it took up more of the screen. Can I just change the image to be, let's go here, size, 500, 500? Let's see what happens. Crop it. Yeah, let me see what happens if I make the image itself square instead of the plot square. I don't know. I'm plotting all of them. I should just plot one. Mirage. I don't know if that helped or hurt. I don't think it helped exactly. Maybe it's fine. I mean, look, I know I'm being a bit... It's fine. It was fine before. Let's just leave it as it was. GNU plot. All right, let's see what it was like before. It's fine. I'll just stick it up there in the corner. It's okay. I mean, like, honestly, this one's also fine. The one that we already have. Maybe I just have that one playing instead. Okay, the 3D one does look a bit cooler. At this point, we're just kind of splitting hairs. It's totally fine. Let's do Mirage. Yeah, why is it so small? Like, whatever. All right, we'll just put it up there. It's fine. All right, we're going to do, let me run Mogrify, and let's get this video also working. I'm going to copy the video that we currently have into a 2D file. So we have 2D.md after this is done, and then we'll have 3D.md, and then we'll have both of them up, and then we'll concatenate them so both show. We could. Yeah, we could. All right, I'm going to run cp test.mp4 into 2d.mp4. And now we're going to run the last /check create video. Yes. And then yes. All right, we're going to remove this video because it is not correct. We're going to have this guy playing, and then let's just watch the whole thing. So let's full screen that guy, and here we go. So it's going to be the same as the 2D video. It's just in 3D now. Obviously, the resolution could be higher. There's a lot of things we could change, but overall, quite happy with it. I think it's fine. You can have progression from 2D to 3D to 4D. To be fair, 4D is going to look identical to 3D. So, like, there isn't much I can do about that one because we're going to have to project it. But we can try the projection stuff tomorrow. I mean, since the N-body stuff is working, and it's actually reasonably fast, I was expecting it to be way slower. I think, I don't know, we might do a number of different things. I'm not sure. Let's just move this up here. That'll do. Okay, looks good, I think. 2 is a bit more illuminating. You can make out the orbits more easily. That's probably fair. Yeah, maybe we have the 2D one playing. It really, either one's fine. I think for now we'll have the 3D one playing, but I like the progression thing better. Okay, so I guess we could concatenate the 2 videos. You're right. We should concatenate the 2 videos. I see what you're saying. I was thinking side by side, but you're saying just put them together. FFmpeg with 2 inputs, adding 2 videos together in FFmpeg, and let's just go over here and let's go mv test .mp4 into 3d.mp4. We don't have the 4D one yet, but we can do that pretty easily. So we can concatenate the videos together. FFmpeg fconcat I list.txt. So if we just do FFmpeg dash f concat dash i 2d.mp4 dash I 3d.mp4 and just say all.mp4. Fconcat. Fconcat. Can I just do this? Let's see what happens. MPV all.mp4. Here's a 2D one. And that's it. Is it possible to individually cover the particles so they're trackable? Yes. I usually do that in like Blender if I'm going to do that. I can find a way to individually cover them in GNU plot stuff. We're doing stuff like super easy right now. The file is video 1 and video 2, but I was hoping to just have the 2 videos like as one command line argument, adding 2 videos together. Cat mylist.txt. Why does everyone put it in a list? Like, can't we just like do? Surely we can just put them together with a single command. We don't have to like create a file for this, do we? Concatenate FFmpeg wiki, join 2 MP4 files on the command line. Perfect. Concat input 1, input 2, input 3. Sure. Okay, let's do that. Dash I, and then it's going to be concat input 1, input 2. Concat, then it's going to be 2d.mp4 and then 3d.mp4, and then we should be able to just run that. No, that didn't work. So it's concat ccopy. No, that didn't work either. That's because that doesn't exist. Concat, oh, there's a colon there. I'm an idiot. Thank you. Yes, let's do it. All right, let's do mpv all.mp4. Here's the 2D result, and the 3D result is not there. Okay, mpv 3d.mp4, that exists. 2d.mp4 also exists. Perfect. So, FFmpeg concat. I'm just going to grab this line. I did something stupid. I'm not sure what I did stupid, but let's see. So, input 2d.mp4, 3d.mp4. MPV output .mp4. 2D results. There is no 3D. Where's the 3D? Okay. I'll remove output. Welcome to Leos Labs, the only channel that promises 4D galaxies but ends up just messing around with FFmpeg the whole time. Let's go here at H. No. Merge multiple videos, FFmpeg single command line input. Everyone's doing the file. Everyone's doing the file. Okay. Concatenating together videos using FFmpeg. Fine, I'll just put them in a file. It's fine. Fine, I'll put them in a file. Gosh darn it. Oh, maybe what I need is -f concat -i. No. Okay, screw it. All right, there they are. They're in their file. What do you want? List.txt, ccopy out.mp4. Let's do it. All right, we're going to call this all.mp4. This is going to be ccopy. This is going to be concat.txt. Okay, perfect. Not.txt. No! God! What's going on? Oh, I see. In the text file. It's .mp4. Thank you. Okay, let's try it one more time. Please. 2d.mp4. File. Okay. Single quotes. Why? Why is everything hard? Like literally everything is just like, come on. Yes. MPV. All the MP4 2D. Okay. Oh, thank goodness. All right, we have it working. We have the 2D and 3D results in the same video. Somehow, getting FFmpeg to work was harder than getting the 3D simulations to work. I don't understand, but whatever. Okay, I will just have this playing on loop, I guess, for just a second while we talk about what's left to do. So today, we got the end body results working. Now, look. Obviously, the scaling here doesn't work very well. If we were to do 1,000 particles instead of 100 particles, we'd run into a lot of problems. So creating a good 2D disk visualization is something we could try. So things that we could do tomorrow, for example, is we could give everything a spin to see if we can create the 2D disk simulations and stuff. But ultimately, I think we are definitely going to have to do some Barnes Hut strategies and stuff like that. So things that I want to do. And I'm not sure exactly what order they come in, but one, we do need to parallelize things, put this on the GPU, make it run faster, all that kind of stuff. Two, we need to make sure that we have some sort of initial conditions to get that disk galaxy working. I'm going to be honest, I would like to find a way to start with initial conditions that are not already rotating. I don't know if that's possible, because I feel like the simulation of just running like a giant cloud and just waiting until some sort of angular momentum hits it enough that it starts rotating, I don't know if that's going to happen, because I think we're going to have some sort of initial rotation, which is really unfortunate. But fine. So I think I need to look into literature, see if I can find like papers that start with initial conditions that are not pre-rotating, because that's something that I haven't seen before, but something that we definitely need to look into. And then obviously there's a lot of gridding stuff. I was super interested in getting like some high quality end body results with different gridding patterns outside of octrees and stuff like that, maybe different clustering schemes, all of that. We'll see where that goes. I mean, this is all stuff that I want to do in the future. So for tomorrow, first of all, I'm going to do some algorithm archive work tomorrow since I didn't do any today, and I really do apologize for that. But we'll come back tomorrow, we'll do some algorithm archive work. Maybe first thing tomorrow we'll do that. In particular, we're working on the Metropolis algorithm, which hopefully will be in by the end of the week. That's my goal. I know it's Wednesday, but I think if we just work on it tomorrow and the next day, of course, it depends on what the what Shadipto and everybody wants. But I think, at least I can do my part by the end of the week, as best as I can. And then tomorrow we'll come back, hopefully do more galaxy simulations, and just really get this thing starting to shine, start running with more particles, getting a lot more visualizations. I've got ideas of how to do the visualization, directly outputting it to images instead of having to plot it differently in GNU Plot, lots of things like that. There's so many just little things to do. And slowly but surely, we should be able to get to that 4D simulation. Questions are, should we do the pre-rotation, all this kind of stuff? we need to solve that. But that's where we are right now. There's a lot of little things to do, and I'm really happy to start tackling them again. If I'm being totally and completely honest, by the way, TFZ1234, thanks for following. If I'm being totally and completely honest, it's been like the story of the stream was way back in the day, like 2016. We were doing a lot of cool simulations like this one, just nice, interesting simulations. And in doing those simulations, I thought we had a lot of fun here on Twitch, but none of those simulations pretty much ever ended up on YouTube. And we ended up talking about like just kind of not boring things, but like the more boring of two options on YouTube. So I think, I'm happy that we're doing these interesting visualizations again. And I'm also happy that we're removing the constraint of having a single video for every algorithm archive chapter, so that as we go forward, we can just do more cool things. And we can just talk about the cool things that we're doing, specifically research focus and stuff like that. So I think I'm going to go ahead and end stream here, since we do have stuff kind of working. I might raid Kitboga again. I know I just spent 4 hours talking, and I'm kind of in the mood where I don't really want to talk to anybody. So I might raid Kitboga again. I've been streaming for about 4 hours. Tomorrow I will start stream a little bit earlier, hopefully go a little bit later. Again, slowly but surely trying to get that stream time increasing more and more. If you couldn't tell, today I've been way more awake and just way more able to speak to people on stream than I was yesterday or the day before. And I think that's just a testament of just doing it more allows for you to make higher quality streams. Like, I just need to break through the barrier where I was like skipping streams and everything and just do it. And I think the more I just do stream, the better the stream quality will be. So with that said, I want to thank you guys so much for watching for the past 4 hours. Some of you guys have been here a long time, other guys maybe not. I'll be back tomorrow, hopefully starting at 2 o'clock Eastern, my time. 2 o'clock my time, which is Central European time. And then we'll go until hopefully 8 o'clock p.m., which is about now. It should be 6 hours. Again, maybe I'll start earlier, but I'm really trying to make sure that I can get that stream stamina up. So it's slowly working towards longer streams. Again, for those of you guys who are in the U.S., tomorrow is Thanksgiving, so I hope you guys are all having a wonderful Thanksgiving, and I will see you guys then. And yeah, have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you guys around next time for the next episode of Leos Labs, where we'll hopefully do more of this stuff and get some cool stuff working. Thanks. See you then. Bye, guys.